So, Masahito, let me know when you want me to start.
Maybe we can start. Maybe.
Okay.
Do the start recording.
Okay, so warm greetings, everyone. And this session, the first talk is by Joe Rennes from ETS Zurich, and the title is Achievable Error Exponents of Compression with Quantum Side Information and Communication over Symmetric Classical Quantum Channels. Joe, yeah, take over. You may take. You are not audible. Joe, you are not audible, I guess.
Yeah, we can't hear you, Joe.
Start recording. Already we started recording. So
We can just stop recording.
How about this? Does this work?
Yes, it is.
Yes, we're good now.
Okay, I don't know what's going on with this one here. Maybe it's not on. Okay.
Yeah, it is working now.
Did we stop?
Okay, very good.
recording?
Sorry. It's recording, I think. So yeah, sorry about the little technical
Why don't we
problems
stop
there.
the recording and start it again?
Oh.
Could someone please stop the recording and then start it again?
Masahito, can you do it?
I am slightly confusing. So of course we already started recording. So then no problem.
How about this? Does this work?
Yes, of course, of course.
Okay, I don't know what's going on with this one here. Maybe it's not on. Okay. Yeah, it is working now. Very good. Sorry. It's recording, I think. So yeah.
Yes, it's
Recording done
recording.
by you, so not to me.
Not
Yes,
sure why
sir.
I'm hearing myself. Yeah, please go ahead.
Please stop the recording and start again. Masahito, can you do it? No, not I'm not doing recording. Only by you making recording. So no problem. By you. So by you, could you stop recording and start again?
Baichu, you, can you please stop recording and start again?
Is he here? Why should
I don't know. And
He is, but maybe I should just start.
All right, but it
Yeah.
sounds like there's some audio in the background. It's,
Yeah, I don't understand that. It's from like a minute ago or something.
yeah, we're like in some weird time loop. All right, I guess just go with it.
All right, good. Let's do it. So, all right, I had a little joke about the very long title, but that doesn't make sense anymore. So welcome to the talk. I want to talk about error exponents. And here's a little snippet from Gallagher's book on the error exponent for channel coding, which you probably all recognize. And so what I'm describing here is some work that's in this recent archive paper. And okay, so just to set the stage, you all know this probably better than I do actually, is if you have a good code, C, we'll just call it, of rate R and block length N for some channel W, then it's good because the error rate decays exponentially when the rate of the code is below the capacity as N it gets very large, right? It should have this form, 2 to the minus N times some constant, which we call the error exponent. Okay, and it's known, like this picture from Gallagher, for classical channels and rates below the capacity, we have these formulas, these upper and lower bounds on the error exponent. And they match sort of the range of optimization there is not quite the same. So at very low rates, they don't quite match anymore. And that's because, as I understand it, you're getting into the regime of zero error communication. And this is causing problems with the sort of information theoretic arguments that don't work so well. But anyway, this is, so the achievability bound is from Fano and Gallagher and others, and the And the upper bound on the error rate is, this is the famous sphere packing bound of Shannon, Gallagher, and Berlekamp. So what about the quantum case? Classical quantum channels, actually, the achievability is not very well, like we don't have good bounds for achievability. So Bernyshev and Holevo showed how to do it for at the same kind of expression as the Gallagher one for pure state channels. So classical quantum channels, the outputs are always pure quantum states. And what is it, 10 years ago or so, Dalai generalized the sphere packing bound to the quantum case. So that has the same form, but we can't really achieve it in general. And it's kind of just an open question there. A little bit weird that, you know, this is like this is the basic thing. We should be able to achieve this. We should be able to match the case for the classical channel. So what I want to tell you in this talk is that we can extend the achievability result from just pure state channels to symmetric channels. And specifically, we're going to use, well, it's going to involve some quantum complementarity, but we're really going to borrow a result on the security exponent for privacy amplification from Hayashi in 2015, and then relate that to information reconciliation or compression with side information. I'll just call it information reconciliation. And from there to channel coding. Okay, and there'll be a few other applications of this kind of method at the end, but the main one is that we can extend this a little bit, at least, to symmetric channels. Symmetric channel, you know, I guess you know what it is, but it's just where if you change the input, say it's a binary input, if you flip the input bit, you can do some unitary on the output and get the corresponding opposite state. So if you had started with 0, you had some output and you said, no, I want the output for 1 at the input instead, you can just apply a unitary to do that. Okay, so that's the kind of symmetric channels we'll be talking about. But actually the main relation between the security exponent and information reconciliation is not restricted to any symmetry. That's just to go to channel coding. Okay, so actually let's work backwards in this. And I'll just try to describe this method a little bit in pictures. Yeah, the argument basically. So working backwards, we want to get to channel coding, but we're going to get there by information reconciliation. So here's, perhaps this is standard to you, or I think of this as kind of a standard thing to do, to reduce information reconciliation or compression with side information to channel coding. So let's start with a channel up there in the upper left. So I guess you can see this. And think of it as actually the n-fold IID version of that channel. Then what you could do is just input uniform, like a uniform random variable to the channel and keep a copy. We'll keep a copy for ourselves and we'll turn this channel into a bipartite source by doing that. It's a very specific source because it's uniform here. And then we can do information reconciliation. We can consider information reconciliation protocol. So what will that look like? The one I want to consider is, that is, we want to reconcile this classical information here, which is uniform, but it's correlated with the output here. So we would like to, you know, the receiver or whoever has this side, the output of the channel, to be able to, you know, to know this value, right? And so if we put this through a hash function, whose output is here, and send it to the decoder, you know, maybe we can build a decoder such that it will output exactly the same value as this one. Now, I want to consider the case where we have a linear hash function, and moreover, it's reversible. So this input here gets split into 2 pieces by this box, and the normal hash function output is going up and over to the decoder. And then what's coming out here is actually just whatever is left that you need to make it reversible. All right. So if it, you know, if it's a n-bit string coming in, the hash function might output a k-bit string, which is less than n. And then this one is going to be n minus k bits in order to make it reversible. I mean, at least you're going to have to do this. Further properties will be required. But this is the idea of it. Okay, so if we have an information reconciliation protocol of that type, you can turn it into channel coding right away, because the error for this scheme is the average over these values here at the output, the hash output that's going to the decoder. And so you just pick the best one and fix that input. That's what I call 0 here. Fix that input to the decoder. Now this box here was reversible, so we can just run it backwards and put in your message to this send it through this is now the encoder, right? Goes through the channel, the decoder. So if the channel, if the information reconciliation protocol is good, then the channel coding scheme will be good. This works for any channel. As I just said, the average error for the channel coding problem. So again, we had uniform randomness here in this conversion to a bipartite source means that now we're considering the case of uniform inputs to the channel coding problem. So its average error will be no worse than the information reconciliation error because we're picking the best value here in that average. The rate of the scheme is it's essentially 1. I'm just saying log base 2. And if the channel, each individual channel has input alphabet size D, so then we have log 2D per channel input, per single channel input. Then the overall rate will be log D minus the rate of information reconciliation. So you can see that here, it's just the size of this one is going to be essentially the size of this thing divided by the size of that one. So then when you take logs, it's just going to be the difference and take the rate, right? Okay, so this scheme can achieve capacity for symmetric channels because you know how to do information reconciliation at its optimal rate, and that actually, when you turn it into a channel coding scheme in this sense, will achieve the capacity when the optimum input distribution is uniform, because that's what we're considering here essentially, and that is the case for symmetric channels. Okay, so now what about connection between privacy amplification and information reconciliation? So this is kind of a reduction, but it can go in both ways in this case. So you imagine here we have a bipartite quantum source. Actually, we're also going to think of the left side more or less as producing a classical output, but don't worry about that for the moment. It could be anything. Then you can purify it to a tripartite source. So it just has this one extra output now, which makes it the whole thing pure. And we have, again, like say, n copies of that thing. Then what we can do is, well, we could consider information reconciliation. So just steal the diagram from the previous page. We have, again, this kind of hash function, make it reversible, and then we try to construct a decoder in this way. And now there's an uncertainty relation. I showed in 2018, actually, that it's basically the uncertainty relation of the min entropy and the max entropy, the conditional min entropy and the conditional max entropy, but it's adapted to this coding scenario, and actually it's an equality. So the normal uncertainty relation is just an inequality. But it's saying that the guessing probability in this scheme up here on the top right, if you consider the output of this A hat, if you consider, so imagine that AN is actually classical. It's, by that I mean it's sort of diagonal and say your favorite basis, I'll call it the Z basis. So then this hash function is just going to act in this basis. That's what we mean by applying it in a quantum sense. And then this output will be some output. Now, if it's possible to recover this value from the decoder, so the decoder gets, like on this side, you can get the same exact value going to the right as you would have going to the left. That's Z hat. Then it must be from uncertainty that actually anything conjugate to Z hat here is completely unknown to the environment, the E system. Okay, so, and in fact, it's this exact equality. So the better you can guess the output here, given these two things, the BN and the hash output, Z check, I call it, Z check is the hash output that you use to, it's like the parity checks. Then that's equal to this fidelity squared. Okay, so it's saying, well, the state here, once it goes to this hash, then the X variable, which is what you'd get by measuring the Fourier conjugate basis instead of in the standard basis. This is a CQ state, and it's very close to the one which is uniform on X, and then there's some independent state on EN. Okay, and it's exactly this relation. So we can use that to go between privacy amplification and information reconciliation, and in fact, we'll just use that to drag the error exponents of privacy amplification over to information reconciliation and then on to coding in the way that I just mentioned. Okay, so here's where we start. We have the security exponent for privacy amplification. So we imagine, again, we have like XN, then it goes through a hash function to become X hat. the eavesdropper holds En, and we're interested in showing that the output of the extractor is close to this product state. And in fact, here it should be close to the one with the exact marginal of the actual state that we have. And Hayashi showed in 2015 that the relative entropy will be close. There'll be an error exponent for this relative entropy of this form, like at least this big, right? Okay, so on the right-hand side, we have the sandwiched Renyi entropy, not optimized, and XA refers to just the X random variable that you would get by measuring just each individual A system in the Fourier conjugate basis. Okay, so we have this conditional entropy. It all looks, this is the usual, the conditional entropy of X given E is what you would expect here. Okay, to get the right Renyi entropy and so on, that's the trick of this kind of bound. But given this bound, we can turn it into an error exponent for information reconciliation right away. So on the left-hand side, that is with this relative entropy here, we just bound the relative entropy by the fidelity. And now we just saw on the previous slide, there's a connection between fidelity of this privacy amplification scenario and the guessing probability. So we then turn that into the error probability of the information reconciliation. We get the following lower bound on the error exponent. So this is the error exponent, this whole thing here for information reconciliation protocols, like how well can you determine Z hat given the parity check, Z check, and En. And it's at least this big, okay? So it's just bounding, converting this relative entropy into this error probability. Okay, so now if we just chain these two inequalities together, we would have a lower bound on the error exponent. But of course, it's in terms of things that have nothing to do with the information reconciliation protocol. So we'd like to get rid of that. So what we can do, now we have to work on the right-hand side. And so this whole thing actually is just a ton of little puzzle pieces that magically, I think, kind of come together right at the last moment. And so now we'll see some of those, the last few pieces coming together. So we already used one uncertainty relation for the left-hand side to say like, okay, this privacy amplification problem is related to information reconciliation, great. But maybe it turns out that if you evaluate the right-hand side for some given information reconciliation task, it's not bound, it's not even very good maybe, or it's just not, I don't know, it's not the form you want. But sort of magically, all the duality relations of Renyi entropies will conspire to give exactly what we want. Okay, so here's what we use in this case. The duality of sandwiched, unoptimized Renyi entropy and the PET's optimized entropy has exactly this form. So this is also shown in this 2018 paper I mentioned. It's really the equality that's shown there, right? Like the inequality that the left-hand side is bigger than the right-hand side is known before, but the equality is also shown in that paper. So now we can replace, we can replace these entropy quantities that have to do with privacy amplification with something that has to do with information reconciliation. So we also have to switch around the rate of privacy amplification. So you see I'll just go back to this slide. So the rate for information reconciliation is talking about the size of this check output, and the rate for privacy amplification is talking about the size of the hat output. And of course, those two, if this is reversible, this product of the sizes of these two is the size of this thing. And so that's how the rates are related in this way here. Okay, so to deal with the right-hand side, we use some Renyi entropy uncertainty relation and this relation about the rates of these protocols by construction. And then down here, it's just what you get when you plug this in. Then you change to the rate of the information reconciliation protocol you're talking about. You have this entropy quantity you want, then you've got to reparameterize it. And this part is just an algebra. But we get a form that, well, it looks like this. Okay, so now we have this maximization for alpha in the range 0.5 to 1 and this particular expression. Okay, so that means we put everything together, we have this achievability result for the error exponent. So the error exponent is at least this big. And now we can compare this with a converse bound, a sphere packing bound from Chang, Hansen, Data, and Say from 2021. And it's the same form, essentially. It's almost exactly like, or if not exactly like, the channel coding case where the achievability and sphere packing bounds they basically have the same form, but the optimization is a slightly different range. And so if the optimization on the sphere packing if the optimal alpha is between 0.5 and 1, then the two bounds match, obviously. Okay, so therefore we've shown that we can actually achieve the sphere packing bound for information reconciliation. And to do that, we had two different uncertainty relations and this construction of transforming privacy amplification into information reconciliation. Okay, so now we want to go to channel coding. Okay, so that was, the sort of, information reconciliation, privacy amplification part. Now we want to go back to the very first thing I said about, okay, we're going to reduce information reconciliation to channel coding. So we had that construction. So now we can take this information reconciliation result and use it for coding. It's only really going to be useful when the when the channel is symmetric, because otherwise we'll get something that, we need to achieve the capacity. We need to make sure that, so the point is that we have a statement in terms of conditional entropy for information reconciliation. And of course, for channel coding, we're going to need some kind of mutual information. And for these two things to be related in a nice way, we need the distribution of the first argument and the conditional entropy to be uniform. That way, they're related in a very nice way. In fact, what's written here in the first equation, so to speak. And so it turns out that for symmetric channels, it's not terribly difficult to prove, but the optimum input distribution for the input to the channel, or for this expression, I should say, this Renyi mutual information, for symmetric channels, it is uniform. And so it will just take exactly this form. It will just reduce to something involving the conditional entropy. Great. So now we have something that involves the conditional entropy. We can just plug it in. So we have also the reduction from the reconciliation protocol to a coding protocol. So we put those pieces together. Now we have a lower bound on the error exponent for the coding problem. And we just plug that in. We use this fact that we have this PETS mutual information that's optimized in the expression. If we rewrite it in terms of this S parameter that's more typical for the error exponent in channels, then it has the form that we wanted to see. So on the very first slide, it was E0 something minus S times R. Well, here's S times R, and this E0 is nothing other than S times this mutual information. So this is what we wanted to prove. So we have lifted this security exponent result to a channel coding exponent. It works for symmetric channels, and we had to use linear coding functions. All these constructions I mentioned, the hash function family was it was linear, and then we made it into a reversible function, which you can do. Once it's linear, you can make it reversible. That's not the problem. But the linear is a restriction, right? We're only talking about linear codes here. Okay, but for achievability, that's fine. We've just shown we can achieve the error exponent that basically matches the sphere packing bound. We use linear codes to do it, but okay, that's fine. Okay, so now there's a few other applications. I should probably slowly wrap up, and in fact, there's only 2 slides left. But I won't spend very much time on this part, just to point out that you can actually go the other direction in this argument. So I said, when I introduced the relation between privacy amplification and reconciliation, that it's not a reduction from one to the other, because it's like a bridge. You can go both ways across this. And so one thing you can do is you can get a slightly sharper bound on for privacy amplification by using a result from information reconciliation. So not only did Cheng and et al. Show the sphere packing bound for reconciliation, they gave polynomial prefactors for it. And then those can go right back over to the privacy amplification problem. And so in the end, what you can show is that the purification distance at the output of the extractor will be, I mean, the sort of exponent for it. Now we're not in the asymptotic limit here anymore. So this first term will be the one that is the asymptotic limit, and then there's the correction terms. And we can inherit those correction terms from the reconciliation protocol over to the privacy amplification. That sharpens a recent result by Li, Yao, and Hayashi. Though again, I have to stress only for linear, since this whole construction is based on linear functions, this is only going to work for linear extractors. Okay. In the interest of time, let me skip this other one. This is also another. You can make a similar statement for strong converse. Open questions in this area, I think. I mean, the main thing is it would be a lot easier if we could just do the duality directly for channels instead of going via privacy amplification and so forth, and information reconciliation. And the restriction to linear functions is also kind of annoying. It would be nice to get rid of that so that then you could just say, this is the way we prove, like we could just use this to prove say the strong converse exponents or anything this way if it were fully general. Okay, thanks a lot for listening, and I guess if you have a question or two, I'm happy to answer.
Yeah. Any questions from the audience?
I have a question. This is Mark speaking. Thanks, Joe, for your talk.
Yeah,
so
thanks.
You've done a lot of work on this kind of topic, including polar codes. Some of the original results there were shown for symmetric channels, and then you had various techniques for extending them to general channels, right?
Right.
Do you think any of those ideas could play a role here?
Actually, I'm not so sure. So there, when you do general channels, I guess for polar codes, it's kind of the polar construction. Well, okay, let me take it back. Maybe you could further specialize to polar codes when you make this kind of argument, and then maybe it's possible to do something. I hadn't really thought about that. That's an interesting idea. That would be like, don't focus just on linear, but now specifically pick polar codes. Could you then say something more? Yeah. That might be possible.
Are they known to, don't they have bad error exponents?
Right. So then you would pick up the sort of, I think they don't have very great error exponents. The newer versions, like the PAC codes, I think are better, but still probably not.
What kind of codes?
So the one that Arikan introduced in his Shannon lecture, which are called PAC codes, I guess, often. So it's basically polar. It's a polar code encoder, but before the message goes into the polar code encoder, it goes through a convolutional code as well, and somehow this fixes all the problems.
Interesting. Thanks.
Yeah.
Yeah. Are there any other questions from audience?
Hello. I have another question. So could you show me that duality relation for that linear divergence, conditional linear entropy? So you have you employ
this one here.
Yes, this one. Oh, this. I'm confused. So what is bar and what is tilde? So which one is best? Which one is
yes. Let me say that again. I probably said it too quickly. The bar one is pets.
Yes.
And the tilde is sandwiched or minimal, or I don't know what it's called. I know that now maybe the notation is different with stars and flats and things, but I don't know those notations yet. Anyway, the up arrow means it's optimized. The marginal is optimized on this one, so you have to use the Simpson inequality, Simpson result, and
so
Simpson.
Marco and Mario consider similar kind of duality relation. But that case is slightly different. So I want to understand that relationship.
Right. So actually the inequality version of this thing, where the left hand side is bigger than the right, would follow from your duality of these two kinds of
our
entropies.
duality equal to 0, but only we have a 3 system, but now you have a 4 system.
No, it's only A, B, and E. It's just that on system A, it's an entropic uncertainty relation of classical information. So on system A, you either measure in one basis or the conjugate basis. So it's still tripartite.
I see.
Yeah, it's still, that's right.
Oh. maybe it's almost same. So once we apply our all the duality relation, then we can derive this equation.
Yes.
Oh,
Right.
thanks. Oh, very much.
Yeah. So that's right. So the only trick that actually I'm not even sure at the moment. Would we even need the equality here for what we want? I'm not sure, but so as I said, the inequality version that's not new to the work I mentioned that I did in 2018. The equality really is like stated there. That's now it's important in the previous step. I'm not actually sure if it's important in this one at the moment. I'd have to check, but.
Interesting.
Okay.
Okay.
I guess I should stop share. Yes, thanks.
Yeah, thank you, Joe. And now we have next talk from Robert Salzman. Yeah. So, should we start? Robert, can you please share your slide? Share your screen if it is.
Yes, I'll do it. Yes, it should be it.
Okay, so the next talk is on total insecurity of communication via strong converse for quantum privacy amplification by Robert Salzman, which is joint work with Nilanjana Datta, both from University of Cambridge. Robert, please go ahead.
Yes, yeah, thank you for the possibility for letting me speak here. Yeah, the title was just said. If you want to have more information about this work, it's on arXiv, and yeah, let me now start. So let me quickly remind everyone about like how you would communicate a classical message if you have a secure key. Everyone knows this, but still to introduce some notation basically. So we have Alice and Bob, they want to communicate this message, or Alice wants to communicate the message to Bob, a classical one. Okay, but there's Eve in the middle, sitting there, tries to understand what the message is. So if Alice now has a key, she can encrypt the message to this MK, right? Bob also has the key. Hope you can kind of see all of the slides that the Zoom window is not blocking. Maybe I put it more here. So if Bob also has the key, he can decode the message from the encrypted message MK. But if Eve has no knowledge of the key K, then both the key and the encrypted message is fully random to her, and she has no means to understand the message, right? So, okay, we're interested in how you could distribute those keys. So classically, I mean, we do this all the time, basically right now, but this distribution solely relies on computation hardness. In the quantum world, that's not the case. So if you allow some quantum communication before like this communication step, like the communication of the message, and Eve has maybe also access to this quantum channel Alice and Bob are using. But if she like there's a measurement on the quantum message sent, she will disturb it, and Alice and Bob have means to find out that someone was there. So because of that, quantum principle, no information without disturbance, we can actually prove information theoretic security results. And okay, the main method for that is obviously quantum key distribution. So I'm focusing on like just the last step of a quantum key distribution protocol, which usually is quantum privacy amplification, right? So here Alice and Bob already share some key, and it's perfectly correlated. Okay, so it's like in some alphabet from 1 to n. It's distributed over some probability distribution P1 to Pn. But there's some side information Eve has. So she has some quantum state, this rho i's, okay? And she, in principle, she can just measure her quantum state and then has some means to guess what the key actually is. So for her to be not able to do that, what Alice and Bob want, they want to decouple from Eve's side information. And usually they want to apply a hash function, so kind of a classical deterministic channel, to reduce to a smaller alphabet, so like m smaller than n. And in the ideal world, they want that, okay, the distribution probabilities for all of those new keys is now uniform, and the side information Eve holds is key independent, right? And in that case, okay, Eve has like no means to get the key apart from just random guessing, right? So like, therefore the key is kind of secret to her if the alphabet is large enough. Okay, let's put this a bit more in mathematical terms. Okay, kind of at that point of the quantum key distribution protocol can be described by the CQ state, where X is held by Alice and also Bob, but I kind of avoid having two classical systems because Alice and Bob at that point share the same system. It's like perfectly correlated and they also do the same things, right? So I just have one X, but Eve has like this quantum side information rho E, which depends on X. So, okay, the hash function is just this F and it results to a new CQ state on some smaller alphabet Z, which I denote by this here. And okay, here kind of in Eve's register, you know, average over all state corresponding to like where you average over all X corresponding to the certain set, that relation here. And you need to be careful. Okay, this here now is a subnormalized state. So if you would normalize it, you would get like some probability distribution in Z, and that would kind of lead to a CQ state in that form, right? So what we want, or what Alice and Bob want, is they want to minimize the decoupling error. So we measure that decoupling error and trace distance is just the distance to the perfectly decoupled state, right? So like on the slide I showed you earlier, that's exactly the situation on the right-hand side. We have uniform distribution, oops, where's my pointer here? Uniform distribution over the classical alphabet and yeah, key independent side information of Eve. And okay, why is that useful? Well, if you look at the optimal probability with which Eve can guess a key, then this is upper bounded by the like random guessing, which is exactly what she would do if like the situation was really just the decoupled state plus the decoupling error, right? So if you make alphabet big and decoupling error small, she has like very, very small guessing probability, and therefore the key is fairly secure. That's roughly the idea. So let us first talk about like the achievability bit of private simplification, right? So if we denote the optimal key length, which kind of is like the largest alphabet Z, such that we can, or I'm looking at the log of that, that's the largest alphabet Z, such that we can distill keys with a decoupling error bounded by this epsilon. Oops, it's should be, that's funny, strictly bigger than 0 and strictly smaller than 1. Sorry about that. Then we don't note this largest log cardinality of Z by L epsilon XE. Okay. And if we're in a situation where Alice and Bob can prepare these states rho XE, and then they prepare kind of many of those, so N IID copies, we are interested possibly in like calculating the optimal key rate, which is just this key length of the big IID state and then divided by N. And we want to understand what happens in the asymptotic limit N to infinity. So there's this famous result, which goes back to Renato Renner's thesis, which tells you, okay, this thing actually has an existing limit independent of epsilon from 0 and 1 here, okay? And it's just given by the conditional von Neumann entropy. And okay, conditional von Neumann entropy is, as you all know, given by the difference of these von Neumann entropies or by the relative entropy in that order. So this is very nice. This is a nice achievability result. We are more interested in the kind of greedy bits. So we think of Alice and Bob like that. Maybe we can distill keys even at a higher rate. If we sacrifice that we get some decoupling error, but maybe we are fine with that, right? We now want to understand how much decoupling error, what really happens to decoupling error in the greedy regime. Okay, so this means if you try to distill keys in an alphabet Zn, which also scales exponentially, but now R is strictly bigger than the conditional von Neumann entropy, right? So okay, the answer is the decoupling error blows up exponentially fast. So the strong converse property holds, right? So you kind of would sacrifice like a lot of decoupling error for getting keys at a higher rate. And formally, this is summarized like in our theorem here, which tells you, okay, like the best possible decoupling error you can make is still asymptotically lower bounded. So this is what I mean with like this curly inequality sign by like 1 minus something which exponentially decays to 0, where the exponent is given by something which really much reminds you of what Joe just had multiple times in his slides. So like this optimization quantity involving now the pets condition for Neumann entropy also non-optimized. So here you have like some way to write the thing down. And okay, you need to know like this, note that this theorem now works for all R. So there's not really a constraint, but kind of it's only interesting if R is large enough, right? So like if you do your standard lovely Renyi entropy tricks, you see, okay, the SCR is strictly positive if and only if R is actually be above the condition of von Neumann entropy, right? So, and otherwise the result doesn't give you like anything interesting. So let us summarize kind of what we know from the earlier work and the strong converse regime. Also, maybe quickly I should mention, because like in that area, I think there was like a lot of work in this year, kind of basically at the same time as our result. There was a result which also looks very similar at like the average case here, the worst case. And very recently, like maybe a month ago, Kelly and Yongxing Yao proved like equality for the exponent. So like kind of here we only have an achievability result, so kind of like a lower bound on the strong converse exponent. They have equality, but in purified distance, and it's interestingly involves the sandwich conditional entropy, but in the range below alpha 1, which kind of hasn't been seen in an operational setting before. So yeah, lots of progress in that area. Really, I just quickly wanted to mention that. So okay, what's the situation? Summarize. So if you plot the decoupling error over the key rate, there's this critical point, so to speak, which is the conditional von Neumann entropy, who below. If you try to distill keys below that conditional von Neumann entropy, the coupling error nicely decays to 0, right? So this is where we are. And kind of you can see from there that, I mean, okay, directly you can see by just the formula I showed you earlier that the guessing probability for E for the key decays to 0. And basically this gives you that the communication using those keys is secure. Our result goes more in the strong converse region. So we are like here, above the conditional von Neumann entropy. So we have this discontinuity, the decoupling error goes to 1, as you can see here, exponentially fast, even as I just showed you in the theorem. However, it's not really clear what this actually means, right? So I mean, it's clear in terms of, okay, if you want to discriminate your CQ state from the decoupled state, okay, and the decoupled state has certain meaning, but it's more kind of, I would think of like a small decoupling error as a sufficient criterion for security of communication. But whether it's necessary condition, it's at least for me, it wasn't really clear. So like whether you might still be able to communicate in some form using keys generated from a CQ state, which has blowing up decoupling error, right? And actually this is not the case. And I want to establish that now, and let me like try to formulate some like framework where this question maybe makes a bit more, like is a bit more meaningful. So yeah, so this is the total insecurity bit in the strong converse region I now want to talk about. We do it slightly more general. So we have like general CQ states, rho z and en like that. But I mean, you can always just think of the resulting state of a privacy amplification protocol, doesn't really matter. And yeah, we want to understand what does it actually mean for communicating with keys generated by the CQ state if the decoupling error blows up, right? Goes to 1 as n goes to infinity. Okay, what's the setup? Alice generates the keys, right, from her CQ state. She wants to encode a message. We say we want M to be taken uniformly out of, like uniformly at random, but out of a subset Mn, out of the like full alphabet. So you have some sub-alphabet. Alice just wants to communicate messages within that sub-alphabet and picks a uniformly at random one of those messages, and then uses the key generated from the CQ state to communicate it to both. Well, the encoded messages will denote by this M subscript key sent publicly, maybe to this notation. So you want that this is like bijective in the key, right? That such that Bob has, if he has the key as well, means to decode it from like the message, decode the message from the encrypted message. And we also want it to be bijective in M. And because the message is sent publicly over like this channel I showed you, the classical channel I showed you at the very first slide, Eve actually has access to this full CQ state. So I call these things in the following message states, right? So it depends on the message sent M. And then you have like a classical register where you average over all the keys. And then you have in the register like the encrypted message. And yeah, Eve has her original side information still hanging around. What Eve wants to do in order to infer the message is to distinguish the states, right? And what's her optimal probability? Well, it's just this guessing probability where she averages where she maximizes over all possible measurements, all possible PUVMs, trying to infer, given that the state was row M, that the message was also M, right? So that's like the standard thing. That's the optimal probability with which she can guess the message. But in order for her to be able to pick actually that PUVM, right, to achieve the optimal guessing probability, she needs to actually have some additional side information, right? And that's exactly knowledge of the subset MN, right? So she needs to know over which sub-alphabet Alice and Bob are trying to communicate. And if she knows that, and she has also knowledge about this ensemble, which she has, then she can pick this PUVM, right? And what we want to now do is try to quantify that additional side information. So essentially the size of MN such that Eve is then able to infer Alice meshes with certainty. And okay, we say if the set MN is small, then the additional side information is large. It makes a lot of sense, right? Because like if the set of meshes is very restricted, Eve already knows quite a bit which messages actually is in the end, right? So we want to quantify how big of an MN Alice and Bob can pick such that Eve is then still able to infer the message with certainty. That's kind of the setup. Okay. So before talking about the strong converse bit, I've tried to like phrase this whole thing more in the achievability region. So what happens in the case one, where uniformly n, the decoupling error is actually bounded by some delta strictly below 1, okay? And then kind of by very standard techniques, like just trace distance bounds, you see like that the guessing probability is bounded by this delta plus a uniform guessing bound over the set of messages. So in particular, this gives you, okay, if like the set of messages blows up as n goes to infinity, which is kind of usually what we would consider, right? Then the guessing probability is actually uniformly bounded by some delta strictly below 1, right? So in that case, Eve has not the possibility to guess the message with certainty, or formulated differently, if she wants to guess the message with certainty, she needs to have very strong side information, meaning that MN is finite uniformly in N, right? And maybe a remark to like to the private simplification bit. So if you think about these rules at N being the resulting state of a privacy amplification protocol, then the decoupling error, like at least in the achievability region, goes to 0, right? So this delta will go to 0, or can be made arbitrarily small for n large. Therefore, this being the case, so if we want p-guess to go to 1 as n goes to infinity, Eve actually needs to know the message beforehand, right? So mn, the cardinality of nm, needs to be 1. So for her to be able to infer the message, she needs to know the message beforehand, and this kind of means that the communication is secure, right? So she needs to know everything to know the message. I don't want to talk about the proof of this thing. I think many people can already guess how you would do that. That's not too interesting. The more interesting bit is kind of really the strong converse region result, where the decoupling error blows up, right? So we want to quantify a bit how the decoupling error blows up. So we introduce the speed of convergence Cn, which goes to 0, and then we say, okay, we assume that this coupling error is lower bounded by 1 minus the speed of convergence. And then the result, which we call like this total insecurity result, really tells you, okay, in this case, for almost all sequences of messages, Mn out of the full alphabet, which satisfies some cardinality bound. So they can blow up. Cn goes to 0, right? So the inverse of Cn obviously goes to infinity. But like for almost all sets of messages where the cardinality blows not up too quick, so it's like strictly below like this blow up, let's say, then the guessing probability in the asymptotic limit of Eve goes to 1. So like for almost all of these still big sets, Eve can guess the message with certainty. She can distinguish all the message states. And relating back to the strong converse region of private simplification, Cn decays exponentially fast to 0. So this means that Eve can infer the message, although it's picked out of an exponentially large set. So she has kind of little extra side information, still large uncertainty about the message itself, just given that she knows the subset of messages, but given her side information and that we're in a regime where the decoupling error blows up, she can infer the message by looking at her at the encrypted message as well as the side information. So I think it's kind of interesting to show a little bit the technical point, how you would prove that, also to like just see what the result means and to not hide it just under these terms. So I would like to try to phrase the proof a bit. So the starting point is obviously like this lower bound here, which is like some suite of convergence bound. And then we just use that and the operation interpretation of the trace distance, right, which is essentially this here, to pick an orthogonal projection, right, pi n, with which we kind of in a symmetric fashion can discriminate the real CQ state and decoupled state fairly well, right? So this here tells you that both the type 1 error, so this here you can maybe think of like 1 minus the type 1 error, so the type 1 error would be smaller than Cn, as well as the type 2 error will be smaller, will also be smaller than Cn for discriminating rho z and En and the decoupled state. Okay, so we pick this this orthogonal projection, and what we now want is to construct two things, right? First, we not want to construct sets of messages which are large, and then a PUVM labeled over the messages within that subset, such that we then can distinguish the message sets, right? And the starting point for creating this PUVM is obviously this pi n. We kind of want to shift that around with messages, and we do that by introducing the unitary UM, which just takes a key and outputs the encrypted message. It works because it's like bijective in M. Therefore, it's unitary. And we can then neatly write down the matches state by just conjugating on the classical part with these unitaries. But we can also write like an M-dependent version of that, of the orthogonal projection, just by the same technique, right? So now we get like all these, for all M in the full alphabet, these orthogonal projections, but they for now don't like give a measurement or somewhere. They are not a measurement. Why? Because obviously they don't have orthogonal support, right? So like they don't sum to 1, they sum to something way, way bigger. So we need to kind of restrict to a subset of messages and then tweak a little bit these orthogonal projections and then create a PUVM out of that. So, okay, let's first try to find like a good set of messages. We know that if we average all message states, we kind of just find the decoupled state. Why? Because we twirl over all these unitaries, right? And then we find like the identity here. And if we sum that up, it's essentially it's exactly the decoupled state. And using this, we can kind of see how we create the sets of messages. And we do that by just picking a random one, right? So I want to say Kn is essentially the size of the sets of messages. I pick like 1 and n, okay? And then I pick like a random vector like that, where each of the components is picked independently and uniformly at random. So if I now look at any k from 1 to this big Kn, and then at the average value over picking these random vectors of this overlap of like the matches state for some mk with the sum of all the other projections, right? So I sum all the messages, the measurement projections corresponding to the measurement messages ML apart from the MK. If I want to evaluate this, this becomes fairly simple, right? Because the random vector is picked in that way that like all the components are independent of each other. So like the sum kind of decouples, it's just this product here, and I have this uniform distribution. Therefore, I can plug in one of the sums, the MK sum, in and use this relation above to just find the decoupled state to the left-hand side. And then the this thing here kind of does not even depend on K anymore, right? Because you have like an identity sitting on a classical register. Those projections are just conjugated, like all the same projections apart from being conjugated with the unitary on the classical register. So this unitary just falls out. This essentially kills the sum, and we're in this situation, right? And now this is the thing I call this type 2 error and discrimination of the decoupled state and the rho Zn, En, CQ state. So this is smaller than Cn, this trace, and then the sum is smaller, obviously, than like the Kn, right? So, okay, to wrap up, we have this average value of somewhat like trying to, it's kind of like a measurement thing, but this is not really measurement. It's kind of like way bigger than a measurement because there's many things which might have non-orthogonal support, but it's kind of like you measure exactly that it's not MK, right? And that error probability, like I'm like in the, how to say, in a very rough way, that's more like in an intuitive way, this thing on average is small if Kn is small, right? So it's smaller than this Kn Cn, and if Kn is smaller than Cn, then this is fine. So this is this. I realize I'm a bit short on time, so maybe I need to kind of skip a bit. But essentially what you now do is you pick, therefore you can pick a set of messages where the Kn is smaller than the inverse of Cn, such that this thing is small as well, right? So this is just because the average is small. And this holds for all epsilon. So like this thing will decay as n goes to infinity. And kind of you just create the PUVM by not picking the pi nm themselves, but you look at the orthogonal projection of like on the support minus, or you cut out kind of the support of the orthogonal complement of all the others. And then this gives you nice PUVM, or this gives you PUVM elements because they sum, because they all have orthogonal support. So they sum to something smaller than 1 and therefore can be extended to a PUVM. And then kind of using very easy tricks, can then see that the guessing probability of Alice sending a message M and Eve correctly identifying it with the PUVM is lower bounded by 1 minus something which goes to 0 as n goes to infinity. So, okay, this is what we have established. Therefore, also on average, her guessing probability goes to 1 as n goes to infinity, right? And I've kind of only talked about how I created one of those sets of messages, but I said
you have 1 minute,
yes.
okay? Yeah.
Yes, that will be enough. Thank you. But like to get it for almost all sets of messages, which was kind of the result, you just do it by a standard Markov inequality argument. So let me quickly wrap up and connect it to the strong converse or to the private simplification bit. So in the achievability region, the decoupling error goes to 0. And this means by our first proposition that the guessing probability can go to 1 if and only if Eve has already perfect knowledge of the message. So the sets of messages is 1. Therefore, we can securely communicate. But in the strong converse region, where R is strictly bigger than the conditional for Neumann entropy, and the decoupling error goes exponentially fast to 1, as we have established, Eve can guess the message with certainty, even if it is picked out of an exponentially large set, right? So she needs to have fairly little extra side information and then is still able to find out the message. And that's, we kind of say that in that regime, you better not use the keys distilled in that regime, because then the communication is totally insecure. Thank you very much for your attention, and sorry for slightly running over.
No, okay, it's fine. Thank you, Robert. Any question from the audience?
Oops.
I have a question. This is
Yes,
Mark.
Hey, Mark.
Hi, Robert. Thanks for your talk. I don't know if this will be worthwhile, but if you dig back in the literature, there are these papers of Horace Ewen. His last name is Y-U-E-N.
Sorry.
there's someone named Horace Ewan.
Okay.
And he has all these papers where he's complaining about security criteria in QKD. And I'm just reminded of it by what you're
Okay.
considering here. And I don't know if it'd be worthwhile for you to take a look at some of those.
Oh yeah. No, sounds very interesting. Maybe
His work was kind of sidelined a bit, and
yeah, okay, no, thank you for
the way that
making
you've
me
thought about this, it just reminds me of that, and so it might be worthwhile.
I might just
take a
shoot
look.
you. I might just shoot you a mail.
Yeah.
That you can then like to get the spelling right. But yeah, thank you for like pointing to that. That might be really
Okay.
interesting. Yes.
I'll put his name in the Zoom chat.
Okay.
Yeah, that would help
Yes.
the audience.
Yes. Yeah, great. Thank you. I noted down.
Any other question from the audience? Hao Chung, please go ahead.
Yes. Hi, Robert.
Hey, good to see you again.
Yeah, good to see you. I have a paper with legal and my student
Yes.
on concourse of privacy amplification, and we also consider trace distance as the error criterion. But we consider one-shot regime, so we also have a one-shot strong converse exponent bound. I'm wondering how to compare our result with yours, but we use different parameterization, so I don't see how to compare them.
So yeah, that was kind of like very interesting because we think like basically both of our papers were like out.
And
no,
also,
it's really,
I use this PATE version, so actually it's the same as yours. H alpha is a PATE version, and we don't optimize the second argument, so we are using the same H. But we use different parameterization in front of this R. So
yeah, but I think I know. So like I know like the formula wise it looks a bit different, but if you kind of reparameterize the thing, you get essentially the same, right? Apart from yours, like the exponent is bigger, so kind of it's a better result because you don't get this 2 here. But I think at least like how it is formulated in your paper, it's like not for the worst case, but it's for like the average case. So like
consider 2 universal hash.
Yes.
And we use totally different approach. Okay, I see.
Yes. So I think actually like for trace distance at least, I mean it's kind of one needs to be a bit careful because now there's like even this tight result for purified distance, which is really recent.
By Wilson and Curry, yes.
Yeah. I was thinking that for trace distance, kind of like the exponent you have, so without the 2 is actually tight. And so, okay, what we do in order to prove that result is we call this like, I mean, this is also then considered in this newer paper by Kelly and Yongxin Yao.
Yes,
but also again for purified distance, kind of like the strong converse exponent for the smooth max relative entropy, right?
Exactly,
so, and we do everything in trace distance and then kind of go to bound to purified distance as well, because that's kind of
relation between trace distance and purified distance. But
and then you get, because like for the private simplification bit, if you because then you like in the H-min, smooth H-min side of things, it kind of works a bit better with purified distance because there's like some I mean it's like there's this open problem in our paper, so maybe I just refer to it because before butchering it verbally, but there's like a lower bound you can have after hashing in purified distance for this smooth H-min, which holds, but it's not clear whether it holds in trace distance. Because we used then just this thing in purified distance, we kind of did the strong converse first in purified distance and then related back with Fuchs-Van der Graaf to trace distance, and that's why we inherited this 2 here. I think if like this H, or if this H-min, smooth H-min inequality is also true for smoothing with trace distance, you would then kind of you could avoid in our paper purified distance as a whole, and then you also find the exponent without the 2, which is kind of the same thing you had.
But I personally think using different criterion will lead to different error exponent or strong converse exponent actually.
Okay. I may have to interrupt. So since we are exceeding time,
sorry.
You may, no, it's fine. You may take discussion later on during break.
Yes, okay.
So now the next speaker is Hao Chung Cheng. Okay. Is recording starting, please?
Bye-bye.
Yeah, so may you please, okay, yeah. So our next speaker is Haocheng Sheng from National Taiwan University, and the talk is on a simple and tighter derivation of achievability for classical communication over quantum channels. Haocheng, please take over.
Thank you very much. And let me thank the organizers again for making this happen. Okay, I'm Haocheng Sheng from National Taiwan University, and this paper can be found on arXiv. Okay, so today I would like to talk about one-shot quantum information processing. And here, I mean, I will not impose specific structures on the underlying states or channels. And there's a general recipe for analyzing one-shot quantum information theoretic tasks. So firstly, we will do a one-shot reduction to a quantum hypothesis testing problem or quantum state discrimination problem. And then we can use some one-shot characterizations of the quantum hypothesis testing, like the hypothesis testing divergence, information spectrum divergence, Rayleigh divergence, smooth entropies, and so on, to see to characterize the operational quantities of interest. And we can also use some asymptotic expansions like the AEP for first order and second order asymptotics to study the second order rate. So the last step is well studied. There are many results. So a general recipe is like if we can obtain a good reduction from the original quantum information theoretic task to a hypothesis testing task, and it's basically done, and we can see how tight it is. We can see it's asymptotic expansion. So that's the most crucial part in one-shot quantum information theory. So how to do a good reduction? Well, it depends on the task, of course. And in this talk, we just discuss a very simple one, the classical quantum channel coding, which we want to send equiprobable message through some code books, and through the classical quantum channel, we make a measurement to guess the message we sent. Okay, and there is a very powerful information spectrum method proposed by Hayashi and Nagaoka in 2003, almost 2 decades ago. And the technical is essentially an operator inequality. It states that for A with eigenvalues in 0 and 1, and for all positive semi-definite operator B, then this holds. And here I use the non-commutative quotient for simplicity. It's just we take B to the 1/2 inverse on both sides. Okay, and this operator inequality holds for any positive scalar C. So this is like a technical lemma to prove an achievability for CQ channel coding and classical communication of the quantum channels for general such channels. Okay, so but it's not obvious how this inequality is applied to prove the achievability, but it's actually a very convenient tool. Okay, but if you use this operator inequality, then those coefficients C and C inverse will show up in your error analysis. And in 2019, Samad, Stefano, and Mark, they published a paper to interpret such an inequality in terms of a quantum union bound. And this quantum union bound was actually studied before, and in this paper, the constant are most sharpened one. So we can see that their coefficients are very similar, like the Hayashi-Nagaoka operator inequality, except for the last one. But if you use this quantum union bound with some sequential decoding proposed by Mark and some auxiliary port systems, you can obtain the same result as using the Hayashi-Nagaoka operator inequality. So there's one way to interpret how this Hayashi-Nagaoka operator inequality works. But to prove this quantum union bound is very non-trivial, and to prove the Hayashi-Nagaoka operator inequality is also a challenge, at least to me. So in this talk, our goal is to provide a conceptually simpler and more intuitive proof for achievability of classical communication of quantum channels by directly using the pretty-good measurement without using other techniques. We'll just use this pretty-good measurement. And as a byproduct, or derived bound actually lead to a slightly tighter one-shot bonds. And also this method can be applied to many other quantum information theoretic tasks with the streamlined proofs. Okay, so that's our goal of this talk. Okay, let's go to our method. Before going to our results, I will introduce some preliminary notations. I will introduce this non-commutative minimum between two operators A and B. We will just search for self-adjoint operator M less than and equal to A and B, and we pick the largest, the one with the largest trace. So it's like a kind of least, greatest lower bounds. We call it non-commutative minimum, at least. And actually, by the Holevo-Hellstrom theorem, they show that such minimum is unique. And for the binary case, actually in their paper, they consider multiple operator case, but in this talk, we will only consider the binary operator case. And for the binary case, this is unique and can be given by this closed form expression. This is an absolute matrix, absolute value function. Okay, and if we take trace on this non-commutative minimum, this infimum representation, it basically meaning that we want to discriminate between A and B, the positive semi-definite operators A and B. This one is like the type 1 error, this is like the type 2 error, and T is the test. And you might think that this looks very strange because we didn't put any constraint on A and B, and they will have probably non-equal trace. The sum of trace A plus trace B might not be 1, but if you take A, for example, like rho times the prior probability and B as sigma times prior probability, it reduced to the usual binary state quantum state discrimination. So actually in the early works of Holevo, he already considers such a very general scenario. So we can interpret this quantity as the minimum error of discrimination between A and B. And if trace A plus trace B is 1, then this reduced to the error probability. And we can also put any like positive cost function for misclassification. So this is like a Bayesian cost or minimum Bayesian risk, something like that. So actually this quantity has an operational meaning. So those works are detailed in early works by Hellstrom in 60s and by Holevo in 72, 74, and 76. And also in Milan and Ordinat's paper, they also study this non-commutative minimum and maximum and prove the uniqueness. Okay, so we will use this formula later. I will use such a interpretation throughout this talk. Okay, and the second property of this non-commutative minimum is that it is monotone increasing. If A prime and B prime is larger than A and B in matrix order, then the trace is getting larger, and it can be seen from the definition itself. Okay, and the third one is that if you put a trace preserving maps, and then if you take trace, and this guy becomes the trace norm, and trace norm is contractive under trace preserving maps, and there's a negation here, so it's getting larger, meaning like if we take a quantum channel on the output state, then the error getting larger, getting difficult for discrimination, and it's just by the properties of the trace norm. And also, this non-commutative minimum is jointly concave on the trace. It's just because that trace distance is a norm, it satisfies the triangle inequality. Okay, and also it satisfies some direct sum properties. It can be seen from this closed form expression. Okay, and there's an upper bound for the non-commutative minimum. So this is proved by Ordinat et al., and it corresponds to the quantum Chernoff bound. And there is a lower bound to this non-commutative minimum by this guy. And again, I use the non-commutative symmetric non-commutative quotient here, B and this A plus B to the power minus 1/2 on both sides. Okay, so what does this mean? Let me take some examples. In the commuting case, we know that the minimum is lower bounded by this guy, the sum divided by the product divided by the sum, and this can be interpreted as a parallel sum for positive, non-negative A and B. Okay, so in the commuting case, it's easy. And let's take another special case, for example, that A and B have equal trace. For example, A is raw density operator, B is sigma. Then recall a well-known theorem by Barnard and Kneel in 2003. They show that the error using pedigree measurement is at most twice of the optimal error. Okay, so let's see the error using pedigree measurement to discriminate equiprobable rho and sigma. Then this is the error probability. We send in rho and the measurement in favor of sigma, and this 1/2 is the prior probability, and for sigma is the same. And then if we use the cyclic property of trace, this guy just equal to this one, and this one is just this lower bound. Okay, and Barnard and Kneel theorem tell us that this less than 2 times the optimal error. What is the optimal error here? It's nothing but the non-commutative minimum between rho and sigma, and it's 1/2 as the prior probability. So we take 2 times 1/2, then the right-hand side is just this non-commutative minimum. So this inequality is a kind of Barnard and Kneel theorem. But in this work, we will use this inequality for general positive symmetric operators A and B. But you can actually adapt Barnard and Kneel's proof to show this. Okay, but I can show you a flavor of this inequality. Okay, so with those basic properties of the non-commutative minimum, we can show our result. So this is our main result, a one-shot achievability. For any classical quantum channel, and there exists an M epsilon code, it means that we are transmitting M equiprobable messages with average error probability epsilon, such that for all probability distribution Px on the input alphabet, such that this inequality holds, epsilon is upper bounded by this guy, where rho xb is the joint state between channel input and output. And because this holds for all probability distributions, we can therefore optimize the right-hand side for all probability distributions. Okay, and we use this non-commutative minimum in the expression. And as I said, the non-commutative minimum is monotonically increasing. So when we take in larger message size, the error will be getting larger. Okay, I will explain this expression through a proof in the next slide. Okay, so given any codebook where each message is mapped to a code in the codebook x1 to the x capital M, we will use the critical measurement corresponding to the channel output, which is like this, pi b given x, where x is every x in the codebook, and the denominator is rho bx, and the denominator is the sum of all the possible channel output states. This is the definition of the critical measurement. So for transmitting each x in the codebook, we will relate the corresponding error probability to this non-commutative one. So the error probability for transmitting x, the state, the error is given by this. The identity minus this POVM element is like this. Okay, and in the this blue one is the transmitted state, and the red part is the other state. So if you take the blue part as A, then the red part, the whole thing as B, then we will use the inequality of related to the non-commutative minimum by this guy. Okay, so we use that inequality we introduced before. So it means that we are discriminating between rho bx and other states. But there's a sum of other states, and the codebook can be arbitrary. So this is actually a mess. It can be very complicated. So we will usually use a random codebook where each code is chosen according to some identical probability. Okay, so we will take expectation on this guy over the possible codebook, and we will use a pairwise independent codebook. We'll first take expectation on the x, and then the other codes given x on this quantity. Okay, so now we want to take this conditional expectation inside the non-commutative minimum, and we show that it is conjunctly concave. So we put this inside, we'll get the second inequality. Okay, and here by linearity, you can move this conditional expectation inside, and because those x bar are not equal to x, and we consider pairwise independent codebook, meaning that for each x bar not equal to x, it is independent to x. So actually we are taking this rho b x bar under this expectation. And this guy is just the rho B, the average state of the output. So in other words, using pairwise independence of the random code books, we obtain this quantity because there are n-1 many other states we want to discriminate it with. Okay, so basically we are done. We take the expectation of X and we are done. It's meaning that we random draw a state and then we discriminate it with n-1 many the marginal states. Okay, but using the direct sum structure of the trace norm, it's equal to this guy. It means that we are discriminate the joint state between channel input and output against n-1 many product of its marginals. Okay, let me use this picture to illustrate it again. So if we want to transmit this x1, rho B x1, and there are a bunch of other states that will cause errors, and we'll choose some POVM element to decide to x1, and also the error is just by the identity minus this pi. If we choose the predicable measurement and you look at this blue part as the transmitted state and all the other parts as a whole thing, then we can see directly from predicable measurement that this M-array hypothesis testing becomes a binary hypothesis testing between rho B x1 against all of the rest, because there's a sum of a rest. This operator is in favor of rho B x1. This operator is in favor of all of the others. Okay, so I call this the one versus the rest classification strategy. Okay, by using the inequality I mentioned before, it can be related to the optimal discrimination between rho B x1 and the sum of the others, where I align them together because they are equiprobable, they are equal weight, and they are n-1, many of them, but they can be arbitrary. So that's why we want to use random code books to average them to the same rho B. So here we can see the rule of the random code books. It makes our life much easier for analyze. So now it becomes this guy, rho B x1 against n-1 many, the marginal states. Then we just take average of it, then it's done, and it goes to the optimal discrimination between the joint state and n-1 many products. Okay, so this is our upper bound. It says that the random coding error is upper bounded by the optimal error of discriminating the joint state against n-1 many, the product of its marginals. So that's our main result. I hope that this proof is simpler and more explainable. Okay, there are some implications of our result. So first, apply the upper bound to the non-commutative minimum, which is just the conventional form. We will get a one-shot error exponent, and the error exponent is expressed by this, the Pate Renyi divergence. And by comparing it to existing one-shot exponential bounds, Banashev and Holevo in 1908 show this one-shot error exponent. It is also one-shot bound for pure state channels, also mentioned by Joe, and they have this constant too. And in 2007, I actually proved also a one-shot bound for general secret channels, and it's a constant 4 here. So we don't have these constants. But in some large deviation regime, we can ignore those constants. But in the one-shot case, we cannot ignore anything. I want to mention that every bit counts, every coefficient matters, because in the one-shot regime, we cannot ignore anything. And by using our methods, and we can extend this bound to the moderate deviation regime, meaning that the rate approach the fundamental limit of mutual information by this speed an approach to 0, but not faster than 1 over square root n. Then we show that this error also vanish sub-exponentially. Okay, by using the infinite representation, we can obtain a lower bound to the message size. In terms of the hypothesis testing divergence defined by this, we just choose the optimal test, attain this quantity, and using the infinite representation, we obtain this bound. As far as I know, this bound is the most tightest one-shot bound so far. By comparing it to the existing results, Hayashi and Nagalka in their early paper, and also Wang Miller, they show this lower bound to the message size, but they have to optimize for those coefficients C and C inverse to get this delta square here. Okay, and also Simon Beckett and Gohari also obtained a bond in terms of the information spectrum divergence. And I want to mention that even in the classical or one-shot case, the hypothesis testing divergence is usually strictly larger than information spectrum divergence. And if we want to go to the second order asymptotics, you have to translate it back to the hypothesis testing. We'll do something delta square here. So those two bonds have the same second order asymptotics. Okay, and we can use a technique by Christopher Trapp and Vincent and Marco to extend this bond to the moderate deviation region where this epsilon is not fixed but approach zero sub-exponentially, then the rate will approach the fundamental limit mutual information at this speed an. Okay, so let me summarize these implications. This is our result, the one-shot achievability. We directly imply this one-shot error exponent bond without choosing any coefficients because there's no coefficients here. And then by the additivity of phase random divergence, it leads to a large deviation region for any Bloch length. It also leads to a asymptotic region of moderate deviation region to show this sub-exponential decay of the error. And so it goes to this lower bound to the message size by this hypothesis testing divergence. And if we expand this hypothesis testing divergence, we get a small deviation regime, the second order terms, and also it leads to a moderate deviation regime in terms of rate. So the left side is all the three one-shot bonds, and the right side is the only IID asymptotics. I hope to provide you a more complete pictures of the achievability, and they all came from this one-shot achievability bond. Okay, so let's take a closer look at this small deviation region. Here I write this minus 1/2 log n explicitly because now we can examine its asymptotics more carefully. Okay, here I want to mention that this second order expansion of the hypothesis testing divergence was proposed by Hayashi and Marco in 2013 and also by Curly. And here I use Curly's bond because it's a bit tightened and it's expressed in this form. There's no third order and it's a fourth order by constant. And actually I have conjecture that this expansion can be a bit tightened by this plus 1/2 log n. That's my conjecture. I don't know how to prove it. But if this is true, then we can get the best possible achievable third order coding rate for general 6 channels by combining our these one-shot bonds and choosing this delta to be 1/√n. And we have this cost of this 1/2 log n, but will be compensated by these terms. Then we will get this lower bound to the message size without any log n. Because previously we will just write a big O log n. But if this was true, then we will get this third order coding rate. I call this the best possible. It's because that in the classical case, this achievable rate is already optimal for some classical channels like symmetric channels and so-called singular channels. So if there's no further assumptions on the channels, this rate is the best possible third order coding rate. Of course, if you put another additional assumptions on the channel, you may get better results, but I think this is the best possible case. So, but we will need this third order expansion achievability for the hypothesis testing divergence. So let's look back to the general recipe for one-shot quantum information theory. Right now, this part, the second part, is a bit tightened. So the bottleneck lies in the last part, the asymptotic expansion of the hypothesis testing. Okay, so to be clear, my intention was not to get a third order coding rate. I wanted to come up with a more simple and conceptually more intuitive proof for achievability. And for a one-shot bond, I want to evaluate how tight it is. So a way is just to evaluate its IID asymptotics. And I found out, we will need a tightened result of the hypothesis testing to evaluate its tightness. So we will need such third order expansion. So it means that still we have room for improvement at the last step. Okay, so I will only have a few minutes. I will go to the entanglement assisted case. I will show that they follow very similar. Okay, so for entanglement assistant case, we will first prepare some entanglement share between Alice and Bob. Alice hold A1 to AN, Bob R1 to Rm, and this small m is the one we want to transmit it. And if we want to transmit this small n, we just send this AM and trace out all the other AM. At the channel output, we have this state depending on small m and all the other share entanglement at Bob. Okay, this is nothing but a position-based encoding by Anurag, Rahul, and Naqib. Okay, and we can observe that if we trace out R1 to the Rm except for R small m, then we will get this quantity will preserve this transmitted channel output state. But if we take trace for the other channel output state, we will get this product of the marginals. Okay, so we will use pre-trigger measurement for this entanglement-assisted classical communications. The pre-trigger measurement is just the formed by the output states. Again, for transmitting each small n, we will relate it. The error probability using pre-trigger measurement, this guy, we take this blue part as A, red part as B, to the one with this non-commutative minimum. Again, this is a sum of a bunch of operators. It's not easy to evaluate. So we take conditional expectation, meaning that we will trace out all the R1 to the Rm except for this R small m, and use the formula here to get our final result. This guy for every small m. So that's our result for entanglement-assisted case. So it's very similar to the CQ channel coding, and we also can see that why we want to use position-based encoding is because that we want to create independence between each message we want to send. It's the same as the random coding in the CQ channel case. Okay, so to summarize the result, we can I formulate it as a one-shot quantum packing lemma for every channel output state. For every state like this, we can have the pre-trigger measurement, and the conditional error can be overbound by this. And to use this result, we can apply to many quantum information theoretic tasks like the classical communication over quantum channels, the entangled assisted one, and the case like quantum channel coding with side information, with channel information at encoder, where we have additional register S and share entanglement between Alice, and the entanglement assisted case with between Alice and Bob, and also the broadcast quantum channel case, entanglement or not, and one-shot multiple access channel coding, entanglement or not, and also quantum data compression and quantum side information. They follow exactly the same way. Okay, I don't have time, so I want to mention that this bound can actually be tightened a bit by putting this. This guy is we call it non-commutative maximum by this. And to prove this inequality is basically follow from data processing inequality from a classical paper and also Joe's early paper. Okay, so actually the bound can be tightened a bit, but I don't like this bound because it looks ugly. But if you want the tightest one-shot bound, our result can be tightened. I just wondering like if this can be used to prove an upper bound for a strong converse exponent by Mosoni Ogawa, and also in recent paper by Yongsen and Kali, they also established the upper bound of the strong converse exponent for several tasks. And they, if I remember correctly, they based on the a classical paper by Corner and Dweck, also in this paper. And can we provide a simpler method for that, because that one is kind of classical. Okay, so let me wrap up. We provide a conceptually simpler and more intuitive one-shot achievability by directly using pre-trigger measurement. You will get a clean and tightened one-shot expressions, and it can be applied to many other protocols. And I want to mention that this is for one-shot achievability for the packing type problems, and actually it has applications for converses of the covering type problems like the privacy amplification that Robert talking about before. Okay, so for bounding the message size, we get a tightest achievable one-shot capacities. For bounding errors, it is a one-shot result, and it cannot achieve the tightest error exponent yet mentioned by Joe. It's a one-shot result, so this still room for improvement. Okay, I will stop here. Thanks for your attention.
Okay, thank you. Any question from the audience?
Sorry, I have a question. So yes. You in your bound, you have a factor m-1.
Yes.
I think this one can be replaced by m-1 divided by 2. Indeed, in the classical case, sometimes we can divide by 2. So this is by using the information spectral method.
Okay, very good question. So if I remember correctly, in the paper in Hayashi and also by Polyansky, Fadu, and Vincent Poole, they show a dependence testing bond. It's an also one-shot achievability bond. So their expression is like, as Hayashi-san mentioned, their one-shot bond is like, there's a of one n-1 over 2 here. So their bond is a bit tightened than this result, but they will use a more complicated method like dependence test or like the information spectrum method. But right now, our proof is so simple, so we can only get this bond. But 1 over 2 is just a bit. If so, it means like we can get a +1 here. In terms of their classical result, the dependence test bond, so they will get +1 here in this result. But here our proof is so simple, so we can only get this. Thanks for the question.
Any other queries or comments from audience?
I have a question.
Yes.
And thanks for a great talk. This was really excellent. Have you, I mean, like you were focusing on pretty good measurement. Did you think at all about the sequential decoding? Like the motivation behind sequential decoding is that maybe you could more easily physically implement that. It's where the pretty good measurement might be hard to do.
Yeah, let's do it.
What's that?
Yeah, I didn't think about that.
I mean, you end up with really beautiful results this way. I don't know if there could be any further improvement of this. It's just more of a curiosity.
Okay, I see. If we want to get the tightest error exponent, maybe we will have to use sequential decoding, because right now this bond, the error exponent is not the tightest one by using pretty good measurement directly. So I do believe that there's still room for improvement. Maybe the sequential decoding will play a role in getting the tightest error exponent. That's my guess, but right now I don't have a result yet.
Okay. And I guess like another curiosity I have is whether your bound in yellow could still be achieved with the sequential decoding. Might be pretty hard to beat.
I think so.
You think so?
Yes, I think so.
Do you have any idea or reason why?
Because actually in your paper of quantum union bond, you use sequential decoding and with Hayashi-Nagaoka operator inequality. So you just use the trick of this conditional expectation over the random code books.
No, but I mean, like what I'm saying is with your bound in yellow, you don't have these constants, C and C inverse, right?
No, yeah.
And it's not clear to me at all whether the sequential decoding method could still get this without those.
You mean sequential?
That would be very interesting.
Okay. With or without the Hayashi Nagaoka operator inequality?
Yeah, I mean, what your work did is you eliminate the need for these extra coefficients and you get this very nice bound.
Yeah, right? Yes, thanks. Yeah, that's because I avoid the step of applying the operator inequality, so we can avoid those coefficients. I guess we have to use the similar idea for sequential decoding as well. Yeah, but it's, yeah, I get your point. It's not clear.
Okay.
But, yeah, thanks.
All right. Well, I'd be interested in talking about that further at some point.
Okay, sure.
Thank you.
Thank
you. Any other question from audience? Okay, I guess there is no further question. Then we thank the speaker. Thank you, Hao-Chung. and all the speakers and participants. Masahito, do you have anything to say?
Okay.
In our country, Stratanovich and myself. But it was not that sophisticated as it is now. And then, of course, for me, it's interesting question. What are applications of this highly sophisticated theory? What do you think?
Yes, of course. Recently, we have a much more close to application, but still far from the real application, because still classical sound theory is slightly far from real application. Because random coding is not so practical, even in the classical case. Because maximum likelihood decoder does not work in practice. So then we need to consider more algebraic construction and somehow calculation complexity for the decoding. So, but quantum communication.
But this is another question. Why quantum information does not go so much in this direction? But there are some work in this direction, but not so advanced as in the classical case.
Not so advanced as classical.
Yes, in classical coding theorem is has plenty of applications, and it is very structured and developed theory. But one cannot say this about quantum case problem.
Somehow depends on topic. So, for example, somehow analysis of secrecy, for example, privacy application, quantum people has more publication than classical person, I think. Depends on topic. Quantum person much more develop more things than classical person, I think. But totally, but somehow, of course, the obtained result in quantum area is not so practical, because it's quite difficult to make sense of practice, because still it is quite difficult to implement quantum communication. So then it
yes, I think this is a fundamental question of implementation of procedures which you develop as theorems, and the question of implementation is much easier and obvious in classical domain, while in quantum domain you have only very few examples of correspondence like homodyne, heterodyne, and energy measurement, I mean photon counting, and
arbitrary POV cannot be implemented.
Yes, yes.
So this is a very serious problem. So.
Yes, yes.
This is
but in theory, in developing theory, you will not move very far without the notion of general notion of POVM, for example.
Yes, yes. So we can enjoy very general POVM in theory.
Yes.
So then we can find the fundamental limit of quantum communication.
Yes,
but
yes.
Still our result is only fundamental.
We can find a fundamental limit, but to how to attain this limit is more question which is closer to practice, and it's not. It's much more difficult, probably, to give at least some approximation for solution of this question.
Maybe channel coding somehow quite difficult. But maybe privacy amplification can be implemented in some sense, I think. Because privacy amplification is somehow very easy because we have a secure state and we can consider it's IID extension and our operation is only application of hash function to that classical data. So this is possible. And somehow even developer have to handle quantum state. So, but this is only virtual existence, virtual player. So we don't need to implement a real even developer. So in this sense, privacy amplification, security by using the privacy amplification can be implemented. So essentially, that kind of part already implemented in some sense in the quantum key distribution. But still, that's experimental part. People is not familiar to this difficult mathematics. So this is a very serious problem. When I talk to some implementation part of QKD, they could not understand my question well. So sometimes I ask, how about the security criteria or how to evaluate security in your implementing QKD, but they could not answer so clearly because that question is too difficult. So sometimes the experimental person does not care that kind of difficult mathematics.
Now, you are physically in China.
Yes. So recently I live in China. So because here somehow almost no duty, so I can spend all my time to research. So very nice.
We must be grateful to our hosts who provided this opportunity for the conference.
Yes, but in China, there is another difficulty for organizing a conference. So they want to keep zero corona policy. So this is quite difficult. So surprisingly, every day I have to take a COVID test. Can you understand? Every day. Every day we have to take COVID test still now. But other countries do not care about the COVID now. This is quite surprising. So, but in the case of China, somehow the quality of medical doctor is quite low compared with other countries. So, in this sense, they are very worried about the risk of COVID still now. So, because in the case of Japan, the student if a student high score, they want to go to the faculty of medicine. So, and they want to become medical doctor. But in China, they are different. They want to go to the computer science or engineering. So that part is much more getting much more money. So, but in Japan, engineer cannot obtain money. So this is a big difference. But in order to develop industry, Chinese strategy is much better than Japanese. So this is somehow a problem. So in Japan, so engineer could not obtain big money. So this is a problem. So By the way, so who is the next session there? So we need to start.
Hi, Professor.
Okay.
Professor Hayashi.
Okay.
Hi.
Thank you very much. So, nice talk.
So I guess it's time to have our first speaker to maybe try to share the screen, share the slides. I guess.
Hello, can you hear me? Hello, can you hear me?
Yes.
Let me see if this.
I guess according to the schedule, the first speaker would be you. Beyond you.
The schedule. Yes.
Last,
yes.
But if you want,
I guess it's
yes.
Where is it?
The schedule got changed a couple of times. I think I was a bit confusing because like at different places there's different things. I'm not entirely sure what the latest schedule is.
I was just looking at the website, so it seems to be.
So if the website is to click on the actual.
It's not. I guess it's not really a big deal who talked first, but I guess let's since both are here, let's just follow the alphabetic order. I guess for the first name, so it should be Akihiro.
Yeah.
Is that fine? So okay.
Yeah. Can I share the slide?
Sure. Sure. Please go ahead.
Can you see my slide?
Good. Yeah.
And
perfect.
Also
so you have yes, perfect. I also see the pointer. Yeah, good. So so you have like 25 minutes, and you have 30 minutes in total, but ideally you should leave maybe 5 minutes for questions.
Okay.
So let's without further ado, let's just get started. Hello everyone. Welcome to the last session of today's Beyond IID. And we have 3 talks for this session. The first talk is delivered by Akihiro Mizutani on computational self-testing for entangled magic states. So please take it away.
Okay, thank you for the introduction. I'm Akihiro Mizutani in Mitsubishi Electric. And today I'm going to talk about computational self-testing for entangled magic state. So this is published in this paper, and the joint work with Hiromasa Aikawa in Mitsubishi Electric and Takeuchi Tani in LTT. So I think this talk is more on the computational computer science side rather than information theory, but I hope all of you are interested in this topic. Okay, so my talk is about self-testing, and in the self-testing there is an unknown quantum device, which is also called prover, and we don't know what's going on inside the device. So this is a completely black box. And our goal is to know the inner working of black box by only the classical verifier. So yeah, here is the classical verifier, and his computational ability is only classical. And to achieve this goal, basically the classical verifier input the classical information into the quantum device and receive the classical information from the quantum device. So by using these input and output statistics, the verifier finally finds that the quantum device prepared the quantum state psi and performed the measurement with the operator M. So in short, the self-testing is a method to certify the state and measurement in the quantum device by using only classical information. So, and in the standard self-testing protocol, there are multiple provers, at least 2 provers, which are spatially separated. And the crucial assumption underlying the standard self-testing protocol is that these provers cannot communicate with each other during the test. So such assumption is very essential because in order to certify that the quantum devices generate entanglement, we execute the test based on typically the Bell's inequality. So if the Bell inequality is violated, then we can find that the devices have non-classical correlations. But such a statement only holds if the devices are spatially separated. So if the devices can communicate during the test, any classical devices can pass such self-testing protocol. So in the standard self-testing protocol, this kind of multi-prover assumption is crucial. So to reduce the number of provers to 1 was an open program. So such a program was solved last year by this quantum paper, Metjan and Bilik. So, and this paper shows that we can self-test a single quantum device. And as I said, in this case, we can no longer rely on varying quality-based self-testing because any classical prover achieves its maximum violation. So we have to consider essentially different situation. And yeah, in this paper, they, instead of assuming multiple provers, they assume a computationally bounded quantum prover. In the standard self-testing protocol, there is no such computational assumption on the provers, and the provers' computational abilities can be unbounded. But here they assume quantum computer operating in polynomial time and cannot solve the running with errors. Okay, so here LWE is short for running with errors. This is a mathematical program used in post-quantum cryptography. So, and LWE is a kind of program to solve a linear equation where small secret noise is added to each equation. So very roughly speaking, we can self-test quantum state if this quantum device cannot break post-quantum cryptography. And in this paper, they showed that we can self-test Bell state, which is one of the stabilizer states. And their protocol is relying on the stabilizer test. I explained the detail about stabilizer test in the later slides. And considering the fact that the self-testing, this single device self-testing protocol is based on the stabilizer test, we can realize that it should be straightforward to extend this previous work to other stabilizer states. Quantum states are, of course, classified into stabilizer states and non-stabilizer states. And the previous work shows that the Bell state can be self-tested with a single quantum device. So, and it could be possible to extend this result to other stabilizer states. Okay, but how to self-test the other class of quantum states, namely non-stabilizer states, was an open program. And basically, our contribution is that we can self-test non-stabilizer states. And in particular, we focus on the CCZ magic state. So this is our contribution. And from now on, I explain our self-testing protocol for CCZ magic state. And before that, I explained the cryptographic primitive used in our protocol in the next 3 slides. The crypt primitive used in our self-testing protocol is trapdoor claw-free function families. They are constructed by Blakelsky and Mahadev in 2018. So basically, if we assume that the quantum computer cannot solve LW program efficiently, then we can construct the function families F and G. So I explain the function family F first. So this is set of function pairs F0 and F1. Here K is public key of LW program. And the important property of this function is 2 to 1. This means that for any image Y, so here Y is the output of function F, and this is a bit string. For given image Y, there exist 2 preimages, X0 and X1, such that this condition holds. So for given Y, there exists the preimage from F0 and F1. And the second property is claw-free property. So this means that the quantum polynomial time prover cannot calculate the preimages from the image Y. So this means that this function is one-way function. So namely, the calculation of left to right is easy, even for the classical computer, but its inverse calculation is hard, even for quantum computer. But if we have trapdoor information, we can invert the image y and obtain the pre-image. Okay, so the trapdoor is a piece of secret information. So this information is possessed only by the classical verifier. So classical verifier can invert the output y by emptying the trapdoor and output and bits. Okay, so only classical verifier can invert the image y and obtain the pre-image x. And the third property of this function family is adaptive hardware bit property. So it's said that the quantum polynomial time prover is how to output these 5 parameters from public key k such that these 2 conditions are satisfied. This means that it is hard to compute one pre-image, here one pre-image, and this in a product. Okay, so here D can be really chosen by the prover. So this means that it's hard to compute one pre-image and any 1-bit information about the other pre-image. So this property is stronger than the aforementioned crow-free property, because if we find 2 crows, we can violate this adaptive hardware bit property. So I explain more detail about this property when I explain our protocol. And the other function family is G. So this is also a set of 2 function pairs. And in contrast to the function family F, this is 1, 2, 1. Namely, there exists only one pre-image such that it outputs the Y. Okay, so basically the set of outputs are completely disjoint. And the important property of this function family is injective invariance property. So it's said that the quantum polytime prover is hard to distinguish between the function families from the given public key k. And like the function family f, so this function is also one-way function. So without the trapdoor information, it is hard even for quantum computer to invert the output. Okay, so using these function families f and g, we construct our self-testing protocol as follows. So recall that our goal is to self-test the CCG magic state. We want to self-test its generation and measurement performed on this state. And first, the protocol is as follows. The first step is that the classical verifier chooses 3 bits, theta 1, theta 2, theta 3, from this set. And if theta is 1, then the verifier generates the public key and trapdoor from function family f. And if theta is 0, then he generates this information from function family z. Again, the trapdoor is a piece of secret information, and this information is possessed by the verifier and kept secret from the prover, and only send public key to the prover via classical channel. And as I said, due to the injective invariance property here, so the prover cannot find which sheeter the verifier chooses. So sorry, here I forgot to say one. So the assumption in this explanation, I here assume the honest quantum prover. So the quantum prover executes the protocol in the honest manner. So we do not, I do not consider the malicious prover. So the honest prover prepares this state. So he calibrates the function output of the function coherently. So here B and X are input of this function. And after the prover generates this state, the prover measures the third register in the computational basis and obtain the outcome Y, so which are sent to the verifier. And after returning the y, the remaining previous state written like this, depending on theta. So if theta is 0, then previous first and second register are in this product state. And if theta is 1, then the previous state is this superposed state. So the reason for obtaining the product state when theta is 0 is that if theta is 0, the verifier chooses the function family G. And G is, one-to-one function. So given image phi, there exists only one preimage. So that's the reason why the prover obtained this product state. So only this XB, only this preimage output that Y. On the other hand, if theta is 1, the verifier uses the function family F. And recall that the function family F is 2-to-1 function. So given the image phi, there exist two preimages, X0 and X1. So this is the reason why we obtain this superposed state. So X0 and X1, X0 and X1 output the Y. Okay. So after prover generate this state, the verifier requests the prover to perform the Z basis measurement. Okay, and the prover measures the first and second register in the Z basis, computational basis, and return the outcomes to the verifier. Okay, so the outcomes are B and XB, and the verifier performs the check. Okay, so verifier checks if these prover's outcomes are correct or not. Okay, correct means that this B and XB satisfy this equation, Y equal Fx. And the failure probability is denoted by PZ. This means that this is a probability of obtaining the wrong outcomes. So this procedure corresponds to the check of prover's Pauli Z basis measurement. And the verifier sometimes requests the prover to perform the X basis measurement. So this X basis measurement check is basically done when the verifier chooses theta equal to 1. And in this case, the prover measures both first and second register in the X basis and returns the X basis measurement outcome to the verifier. So specifically, if the second register is measured in the X basis, then the prover obtains the outcome D. After obtaining this D, the first qubit state is written like this. Okay, so this is either ket plus or ket minus, depending on this exponent. Okay, so this exponent is denoted by M. So of course, if we measure this state in the X basis, then we can obtain this exponent. So the provers send the verifier the first X basis measurement result and the second X basis measurement result. Okay, so and the prover performs the check of X basis measurement. Specifically, the prover uses the trapdoor information and check if these outcomes are equal to this one. Okay, so this is the honest case. So the prover always pass this check. Okay, but to consider the general case, I denote the failure probability of obtaining the wrong outcome by PX. So I make some remark about the adaptive hardcoded property that I explained minutes ago. Again, this is the property that the contemporary prover is had to output these 5 parameters such that these 2 conditions are satisfied. So this property holds for any polynomial time quantum prover. So of course, this condition holds for honest quantum prover. So honest quantum prover means the strategy that I explained so far. But the honest prover more specifically, the honest prover satisfied either of the two conditions. Okay, so by measuring the state in the Z basis, then the honest prover can satisfy this left condition. On the other hand, the honest prover performed the X basis measurement, then he can satisfy the right condition. Okay, so it is easy for efficient quantum computer to satisfy either of the two conditions, but it's impossible to satisfy both of these conditions due to the hardness of LW program. Okay, so far I explained the checks of prover's X basis measurement and Z basis measurement. Using this kind of information, we execute the test of generation of CCZ magic state. So this is a target state in your self-testing. So this check is done when the verifier chooses theta as all 1. And after prover returns the outcomes of image Y and X basis measurement of the second qubit, second register, the prover's state is written like this blue state. Okay, so this is the 3-qubit state. 3-qubit state in the X basis eigenstate. Okay, so after prover generates this state, the prover performs the controlled Z operation and obtain the target CCZ magic state. And the classical verifier requests the prover to perform the generalized stabilizer test, and the prover measures each of the 3 qubits with the generalized stabilizer and obtain the outcome V. And the prover returns these outcomes to the verifier. Okay, so and using the trapdoor, the verifier checks these outcomes are correct. Okay, so and P denotes the failure probability of obtaining the wrong outcomes. Okay, so I explain more about this generalized stabilizer test. So of course, the CCZ magic state is not a stabilizer state. So this state cannot be stabilized by Pauli operator. But of course, any pure state, psi, is stabilized by some Hermitian operators. Okay, so I call these Hermitian operators generalized stabilizers, and we denote them GI. Okay, so GI is written like this. And specifically, the generalized stabilizers of CCZ magic state are G1 and G2 and G3, and G1 is written as X tensor CZ. And G2 and G3 are the similar operator, where X is the position of X is shifted to the second and third qubit. And the generalized stabilizer test means that the verifier checks the measurement outcomes of these generalized stabilizers. But here there is a CZ in the generalized stabilizers. So by naively thinking, if we measure the outcomes of this generalized stabilizer of the CCZ magic state, 2-qubit gate is needed. Okay, so but this is not, such a 2-qubit gate is not needed by using this PRX paper. Okay, so the crux of this paper is to decompose the generalized stabilizers into the Pauli operators and projectors. And the prover measured each qubit in the Pauli basis. Okay, so specifically the prover measures the first qubit in the X basis and the second and third qubit in the Z basis. And the prover obtains the outcomes V. And the prover sends the outcomes to the verifier. Okay, so and verifier checks whether this condition holds. Here M is the bit information that verifier only knows. So if this condition holds, the verifier finally finds that the prover generates the state, which is the +1 eigenstate of X tensor CZ. So using only the Pauli operator, Pauli measurement, we can measure the generalized stabilizer of CCZ magic state. And as I explained, the verifier checks the Z and X spaces measurement. And using this information, verifier knows how accurately the prover performed the generalized stabilizer measurements. So by checking the outcomes of generalized stabilizers, the verifier finally finds the distance, lower bound on the distance of rho and target state. So here rho is the general prover's state after returning the information of D. So, okay, so now I explain our main result. So I explained the theorem. The previous failure probability of Z and X basis measurement and generalized stabilizer measurements are denoted by these parameters. And we denote the previous Hilbert space by H. Okay, so in this setting, there exists an isometry V and some quantum states theta and constant R, such that for any general previous state rho, the following two statements hold. Okay, so as for the result of the self-testing of state, by running the protocol, the verifier finally finds the upper bound on the trace distance between the previous state and the ideal state. Here, V is the isometry that corresponds to the extraction operation of 3 qubit. Okay, and this P can be obtained by running the protocol many times. So if the previous behavior deviates from the ideal behavior more and more, then this probability gets larger, and hence this upper bound is also larger. Okay, so as for the result of self-testing of state and measurement, by running the protocol, verifier finally finds the difference of these two probabilities, upper bound on the difference of these probabilities. Okay, so this probability this is a distribution of outputting the outcome V when prover measures the state according to the request parameter Q. So this is the actual probability, and the right one is the ideal probability. So this is a probability of outputting outcome V when the target CCZ magic state is measured in the Z or X spaces according to this request parameter Q. Okay, so I wrap up my talk. Our contribution is that using the crypto technique, trapdoor growth-free function families, we revealed that one of the non-stabilizer state, CCZ magic state, can also be self-tested with a single quantum device setting. I end my talk with some future work. The first future work is to self-test the state where all the Pauli operators appear in their generalized stabilizers. Okay, so if only X and Z appear in the generalized stabilizer, I think it's single device self-testing seems possible. But it seems difficult to solve this program because we have trapdoor growth-free function families that are composed of only 2 function families, F and G. So another future work is to self-test in non-IID scenario. So here we assume the previous behaviors is the same for each repetition. So, but it's of course interesting to consider whether it is possible to extend to non-IID scenario by using the definitive theorem or one-shot self-testing. Okay, so this is the end of my talk, and thank you for your attention.
Thanks for the very nice talk. So is there any question in the audience? If you have any question, just
hello, I have a question. So
yeah.
You use flow-free function. So I want to understand its definition, and also what is flow? Flow
means there exist 2 preimages that output the same Y. This is a crow. Yeah.
kind of collision.
Yeah, yes.
Collision free in some sense.
Yeah. In other words, yes. And I'm interested in the definition of trapdoor group-free function families.
So Professor Hash, do you have more to ask?
Okay, I understand. Okay.
Yes. Is there any other question? Maybe I was just wondering, so what is, like at some stage you mentioned that you assume the prover is honest, right? So can you just elaborate a bit more, like what would happen if the prover is not honest? Or, like what's the thing that kind of makes proof won't work?
Okay, so for in the protocol description, I assume that the prover is honest, but I'm sorry. this result holds for any quantum polynomial time prover. So yeah.
So don't really have to assume that.
Yeah.
In some sense. Okay, great. Is there any more question? I think if not, we can let's thank the speaker again, and we kind of proceed to the next.
Okay,
talk.
thank you very much.
Thank you. So yeah, don't you may share your slides? Yes. Okay. Yeah. Can you see it? Perfect. Yeah. Okay. Good. So let's get started. So our second speaker is Yadong Wu from the University of Hong Kong, and he will be talking about detecting quantum capacities of continuous variable quantum channels. So Yadong, please take it away.
Thanks, Yuxiang. Thanks for all the organizers of this conference. Here I'm going to talk about how to detect quantum capacities over a continuous variable quantum channel. So this is a joint work with my supervisor, Julie Bella, and I'm currently a postdoctor working at Hong Kong University Computer Science Department. I'm going to talk about how to benchmark or test capacity over a quantum communication channel or a quantum memory device. So both these quantum communication channel and the quantum memory device is a very important component in a quantum network. And to assess the performance of these quantum devices, the central figure of merit for these devices, their quantum capacity. It quantifies how many qubits we can transmit or store per use of this device in principle with optimal encoding and decoding. To assess a realistic implementation of this quantum device, we need some protocol to estimate the quantum capacity only from the experimental data. So another motivation here of our paper is we try to find some connection connect the quantum information theory with a real quantum experiment. So in quantum information theory, we have many of these rigorous mathematical information concepts like capacity, entropy. So different quantities may have different operational meaning in various quantum information processing tasks. Then on the other side, we have in a lab, we have some uncharacterized noisy quantum channel. We may have some probe quantum state, and we may perform some feasible quantum measurements. So usually, people who care about quantum information theory and people who care about the experiments are two groups of people. But here, in this paper, I try to propose a protocol which we think can be experimentally implementable to detect certain the one-shot quantum capacity over an uncharacterized noisy quantum channel. So this task may look similar to quantum process tomography because in both cases we want to learn some information from the measurement data about this unknown quantum process. But here, instead of fully reconstructing the quantum process, we only care about how many qubits can be transmitted over this quantum channel. That is, we only care about detecting its quantum capacity. So some difficulties in detecting quantum capacity to explicitly calculate the quantum capacity is very tough in the most general case. So it involves a difficult optimization, and which can be done not. So without the assumption of very simple noise model, we cannot give the explicit calculation expression for the quantum capacity. Then to calculate the quantum capacity also require us to have a classical description of this quantum device. But this requires us to perform quantum process tomography. And as we know, process tomography is a really resource-consuming process. So for the sample complexity can scale exponentially with respect to the number of qubits. And we also want to consider the most general scenario, that is, in each use of this quantum device, the noise can keep fluctuate with respect to time, and also the device can there can exist correlations between the noises in each use of this across these multiple uses of the quantum communication device or quantum memory device. And even this quantum communication channel can be under control of an adversary during the communication between Alice and the Bob. And in this paper, we will focus on continuous variable quantum information that is encoded in quantized electromagnetic field or quantum harmonic oscillator. And it has an infinite dimensional Hilbert space spanned by this quantum number n from 0 to infinity. And if we measure the position or momentum, the outcome has a continuous spectrum. And the continuous variable system is also an important platform for realization of quantum technologies. Let me try to summarize what I have done in this work. So we proposed two protocols to estimate lower bounds on the quantum capacity over a continuous variable quantum channel. And these protocols are fit in the realistic scenario, that is, the number of uses of the channel device is finite. And the first protocol is for the general non-IID noise, that is, the noise can keep changing. There can exist correlation between multiple uses of the device. And the second protocol is for certain particular type of IID noise. For the non-IID noise model, we have this, so we use this, in the figure, we use this big box to represent some certain mode quantum channel, but in what channel it is, we don't know what is inside this box. Then we randomly pick some modes as the input to as our test modes, and the remaining modes are used for the purpose of communication or storage. And the corresponding test output modes, we perform quantum measurements and send this classical outcome to do some information processing to decide whether to pass this test or fail. So if we pass this test, then we will infer a lower bound on the quantum capacity over the remaining modes used for communication with certain high confidence level. Note that this lower bound is just a statistical inference result. It's not a derived lower bound on quantum capacity for some known characterized quantum channel. And an example for this claim about after we passing this test is we may say the average quantum capacity per mode is certified to be no less than 1.3 with certain high confidence level, 99.9%. Here, this 1.3 is our lower bound on the quantum capacity given in this test protocol, and this confidence level is some parameter we can tune in this protocol. Otherwise, if we fail the test, then we have no conclusion on the what is the quantum capacity over the remaining over the other uses of the device. It means that we simply don't trust this quantum device anymore for communication or storage. Here, since we considered finite uses of the quantum channel, so we, instead of considering the asymptotic quantum capacity, we will consider the one-shot quantum capacity. So for a n-mode quantum channel E, the one-shot quantum capacity with respect to a certain error epsilon is just the maximum number of qubits that can be transmitted over E with optimal encoding and decoding, and with the error in the maximal infidelity smaller than epsilon. Here B is just the dimension of the encoded Hilbert space, and D is the optimal decoding, and phi is the encoded state. F E B represents denotes the maximal fidelity between the encoded input and the decoded output. In the special case, when this n-mode quantum channel is just copies of the same noisy channel, then the asymptotic quantum we can achieve the asymptotic quantum capacity by making this n goes to infinity and the epsilon goes to 0. So here we consider one-shot quantum capacity because for one-shot quantum capacity we can consider the arbitrary correlated noise between among multiple uses of the channel device, and we can consider finite number of uses of this device, and the decoded information, the fidelity we can have a non-zero error in our decoded information. So due to these reasons, we will try to detect a lower bound on the one-shot quantum capacity over multi-mode quantum channel. So for suppose this channel is denoted by En, representing n-mode unknown quantum channel, and the input state denoted by sigma. The input system is A prime. A purification of the sigma is capital denoted by capital psi. Then at the output side, the joint state at both the input and the reference modes are denoted by rho. With the output state denoted by B and the reference denoted by A. Previous result has shown that the one-shot quantum capacity can be lower bounded by such an expression. Here, eta is a small parameter between 0 and the square root of epsilon over 2. Then this smooth max entropy over unknown state to n-mode state rho is just the minimum of the max entropy over state rho inside a small neighborhood of around the rho. Then to estimate a lower bound of one-shot quantum capacity over E is simply reduced to estimate a bound on this smooth max entropy of unknown state rho. Since this inequality is true for all the input state sigma, we can simply choose some state which is experimentally feasible to easy to prepare. Here we choose this n-mode input state to be copies of thermal single mode thermal states, and the purification of a thermal state is just a two-mode squeezed vacuum state. So one mode of the two-mode squeezed state is fed into the noisy channel, and the other mode is kept as a reference mode. Then given n-mode channel, we randomly select the k modes for the purpose of test. Then the task is to estimate the lower the bound on the smooth max entropy at the 2 times n minus k mode state rho. And this estimation of the max smooth max entropy of over this quantum state can be reduced to estimation of max entropy over a classical quantum state obtained by performing quantum measurements at the reference modes. So here, for each reference mode, we randomly select to perform our quantum measurement into one of the two conjugate measurement bases. So we randomly either to mirror the moment position or with a half probability to mirror the momentum. Then the classical outcome system is denoted by X. The classical quantum state is denoted by omega. By using the entropic uncertainty relation, we can find this inequality to bound this smooth max entropy of quantum state by a smooth max entropy of the classical quantum state plus two constant terms. Here, the parameter xi and xi prime should satisfy this equality. And the parameter d denotes the discretization width of our continuous outcome. So remind that the measurement outcome is theoretically is a continuous outcome, but in realistic scenario, we only have finite resolution, so we must have this d larger than 0. That is the discretization width of the this continuous outcome. Then to estimate, the problem is reduced to estimate the bound on this smooth max entropy of this classical quantum state omega. And this can be further bounded by performing some correlation test, that is to perform same quantum measurements at the corresponding output test mode, then compare the correlation between the pair of output mode and the reference mode. If there is a strong correlation between these two outcomes, then the max conditional entropy should of this state omega should be upper bounded by a certain function of the correlation between the two outcomes. And then we can further lower bound the one-shot quantum capacity over the other n minus k uses of the quantum channels. And this entanglement-based detection protocol is equivalent to the following measurement prepare and measurement protocol. So in this prepare and measurement protocol, Alice as a sender, she prepares at each test mode, she either prepare a position squeeze the state or squeeze the state at position basis or momentum basis. Then he apply a displacement operation with amount of displacement is sampled or a discretized Gaussian distribution. And at the corresponding output side, Bob performed this projective measurement, obtaining measurement outcome XP. Then they calculate the distance between these two values, XA and XB, average over all the K test modes, then compare it with a certain threshold. If this average distance is less than a certain threshold, then we pass this test, and we can obtain an infer lower bound on how many qubits that can be transmitted over the other remaining n minus uses of the channel with certain small error probability. So here, if we want to increase our infer lower bound on the quantum capacity, we can reduce the value of this threshold T. But at the same time, by reducing this threshold T, we will make the test harder to pass. So there is a trade-off of this choosing the threshold. And the transmission for the purpose of quantum communication or quantum storage can be achieved by feeding half of a two-mode squeezed state into each use of n-1 channels. Then we are done with the non-IID protocol, and I'm going to talk about the second protocol that is for the identical and independent noise. So in this case, the mode channel is just copies of a single mode noise channel. And again, we choose our input state to be two-mode squeeze vacuum state. And at the output side, we have n copies of state, unknown state tau. And then asymptotic equipartition property tells us that this max entropy over n copies of tau can be upper bounded by n times the conditional entropy or a conditioned B over the state tau plus certain small term. And plugging this inequality to our first inequality of the one-shot quantum capacity, we obtain the following inequality, and the estimation of lower bound on one-shot quantum capacity is reduced to estimate this conditional entropy. And to estimate this conditional entropy, here we add two more assumptions on the noise. So we first assume this channel is a Gaussian channel, that is preserve the Gaussianity of the input state. Then the second assumption is this channel is a phase insensitive channel, that is, it always commutes with any unitary any phase rotation unitary operation. And under these two assumptions, the estimation of this conditional entropy can be reduced to estimate only the variance of the cogenitor at the reference mode and the output mode, together with the covariance between these two cogenitors. And again, this entanglement-based protocol is equivalent to a certain prepare and measurement protocol. And here the advantage is that we don't need to prepare squeezed state because we don't use any uncertainty principle. We just prepare coherent state, which is much easier to be implemented. And at the input side, Alice first prepares certain vacuum state and apply a displacement operation with amount of displacement sampled from a flat distribution denoted by X. And at the corresponding output side, Bob performs measurement in the coherent state basis, obtain outcome Y. Then they calculate the cross correlation between X, the values of X and Y, as well as how much amount of noise is added by the channel in by estimating the variance of y. Then higher cross correlation between these two values of x and y, together with a lower added noise in y, will indicate a higher values of quantum capacity. And we also did some numerical simulation on our result, using our theoretical bounds. And this figure shows the bound on the one-shot quantum capacity per channel versus the number of uses of the channel device. So I want to talk about the detail of the numerical simulation, but there are 3 points we learned from this numerical simulation. The first is we find that the lower bound given by the IID protocol, the second protocol, converted much faster to the asymptotic limit compared than the general protocol. So it means the general protocol really consumes much more sample complexity to achieve a non-trivial lower bound on the one-shot quantum capacity. And the second, in the general protocol to detect quantum capacity, if we want to raise the inferred lower bound, we must increase the ratio of the numbers of modes used for testing. Or we can reduce the discretization with D. That's the equivalent. We can say we need to increase the resolution, the accuracy of our measurement device, or we can reduce the threshold. But by reducing the threshold, we may make the test harder to pass. And thirdly, another important parameter I have not mentioned is the cutoff parameter. That is, if the measurement outcome exceeds from negative alpha to positive alpha, then we just take the value to be either negative alpha or positive alpha. So this cutoff value should be large enough to make sure we get a non-trivial lower bound. Otherwise, as the pink curve shows, when this n goes to large, we may give a trivial lower bound if this alpha is not large enough. Then this is the summary of my talk. So we proposed 2 protocols to estimate lower bounds on quantum capacity over a continuous variable quantum channel simply only from experimental data. And the first protocol is for the general non-IID scenario, and the second protocol for particular IID noise. And both protocols can be implemented using the current technology on optical platforms. And they can be used to validate practical quantum communication devices or quantum memory device. And in the near future, we may use this protocol to detect useful communication paths in a dynamically changing quantum network. That's all for my talk. Thanks.
Thank you, Yadong, for the very interesting talk. Any question in the audience? Any question? So maybe I was wondering, maybe something into the technical details. I was wondering if you achieve for the proof of non-IID case, whether you achieve that by using some type of, I don't know, quantum definity theorem for continuous variable channels or states. And if so, can we ask what is the concrete role of, let's say, energy of the input here in this task? Because, in the continuous variable version, I guess the dimensions should be replaced by some theoretical energy and also maybe the arrow measure. So may I ask whether there is relation between the energy in the, let's say, the input state you use for tests and the precision of your
yes.
outcome?
So yes, the energy it does affect a lot in the infer the lower bound. So we didn't show the expression for the lower bound, but actually it does affect. And we did some numerical simulation, and it makes sense. Then if we have higher energy in our input state, we can get a higher inferred lower bound. And actually, alpha is another parameter. We make this cutoff. We make this truncation in this measurement outcome. So this alpha must be large enough. Otherwise, we may give a trivial lower bound on the expression of the lower bound may become just equal to 0 if this cutoff is not large enough.
I see. So did you really use subcontinuous variable definity theorem, or did you just use maybe the finite dimensional one using cutoff?
No, we didn't use definity theorem here. So actually, at the beginning of this project, I thought about using definity theorem, but after I derive a lower bound using definity theorem, and then I compared that bound with the bound here in the first protocol, I find that actually this bound scales much better than the bound derived from definity theorem.
I see. Interesting.
No. Thanks.
Any other question? I guess if not, let's maybe thanks Yadong again, and let's proceed to our next speaker. Thanks.
Can you hear me? Hello?
Yes, I can hear you.
Okay.
Yeah, slide seems to be working. Very well. So let's get started. So I guess it's the last talk of the day. So this a talk delivered by Beyond IID, who will talk about parallelization of sequential quantum channel discrimination in a non-asymptotic region. So Beyond, please take it away.
Yeah, thank you very much. So I'll be talking a bit about how one can compare parallel and adaptive strategies in quantum channel discrimination when one only has a finite number of channel users and not in the asymptotic limit. And this is joint work with Lanjana Datta and Robert Salzman from Cambridge and Mark Wilde from Cornell. So to start with, let me maybe introduce the task a bit. So what is quantum channel discrimination? The idea is the following: somebody gives you a black box, which is a channel. So essentially, like, you can put in a state and you're going to get out a quantum state. And he promises you that this black box acts as one of two channels. So like it either works as a channel E or the channel F. And I'm going to use kind of this notation with this bar in the middle to denote that. And the task is to find out which channel actually sits in the black box. And let's say you're kind of the process of finding out, you're allowed to use this black box a finite number of times, let's say n. And if you want to do this, kind of, you have to figure out which input states you want to choose for this black box. And in general, maybe, since you can use the black box n times, the input states you choose could depend on the output states of previous black box users. And for some reason, no, this works. It's not that hard to see then that kind of the most general thing you can do is something like this, where, okay, what do? You start with an entangled input state on the left, where kind of half of it you put to your first channel use. And then based on what you get out and based on kind of what you have in the other half of your entangled input state, so usually we call this the memory or the reference system. Based on these two things, you're going to kind of apply some quantum operation which prepares the next input state and then also maybe changes your reference system or your memory a bit. And then you can keep doing this n times, where you use the black box n times. And in the end, you will arrive at some state in both the output system of your black box and also what you have stored in your memory reference system. And then you're going to do some kind of measurement to decide on what you think actually is in the black box. And so in general, the input states here are going to depend on previous channel outputs, and so this is why this is called an adaptive strategy. And also let me introduce the notation here. So I'm going to write rho I or sigma A for the state at this stage before I use the channel for the ith time. And I'm going to call it rho I if my black box actually happens to be E. I'm going to call it sigma I if my black box happens to be F. And okay, for the first time, because I haven't used my black box yet, they're going to be the same. But then later on, they're going to be different based on what's actually in my black box. This is kind of a fairly complicated setup because I have these kind of essentially arbitrary preparation channels in between of each use. So you could say, okay, why don't I do something very simpler? This is what is called a parallel strategy, where essentially the input states don't depend on the previous channel outputs. So what you do, you pick some joint input state, which has n input systems and then some reference and memory system. And kind of each of these n input system you feed into one copy of your channel, or essentially kind of these are the n uses of your black box. In the end, you're going to get some state again to which you apply measurement. And one thing one kind of can see fairly easily with this kind of setup is that if you do something like this, you can restrict the size of your memory system or your reference system to be as large as all the input system, whereas in this adaptive setup, it's actually not so clear whether there's really any bound on the size of this reference or memory system. In principle, it might be advantageous to make it arbitrarily large. And it's also not so hard to see that every of these parallel strategies I can write as an adaptive strategy, basically by just kind of putting my joint input state in the memory system and then feeding out one copy with each of these preparation operations. So this is kind of a way simpler setup. Now the question is a bit, okay, how good is this? And people have been able to show in certain scenarios that actually asymptotically, in some sense, which I'll describe in a second, these parallel strategies are optimal. And so kind of this is kind of the general overarching question: to what degree are these parallel strategies good enough? So I haven't really stated yet in what sense I kind of want to, what optimal means. So I have to talk a bit about errors. And for this, let me kind of very briefly talk about discriminating states, because, as I just tried to explain, at the end, when you do all these, when you use your channel n times, at the end, you'll arrive at some kind of state discrimination problem. So how do we discriminate states? So, I mean, the way you essentially discriminate states is you do a binary POVM. This is the most general thing you can do, where measuring each of these two elements corresponds to you claiming that your state is either rho or sigma. So the first element, which I write as pi, is going to be associated to claiming that you have the first options, in this case, the state rho, and then you're going to make two types of errors. You can make the error that your state is sigma, even though your state is actually rho. This is going to happen with this probability. And you can make the error that your state is the claim that your state is rho, even though it actually is sigma. This can happen with this probability. The second one we call the type 2 error, and the first we call the type 1 error. And you can see that depending on what you choose as your measurement operator, your PVM here, you can have some kind of trade-off between these errors. For example, if you choose it to be 0, then one of these is going to be 0, the other one is going to be 1. So you can kind of decide a bit on which of these errors you want to minimize. And there's no kind of different settings which one can look at these discrimination problems. And one of them would be to say, okay, I want to minimize like the average error or the sum of these two errors. What we'll be looking at instead is at the asymmetric setting, where we say, okay, we want to minimize the type 2 error, so this thing, make it as small as we possibly can, under the constraint that the type 1 error, which is this thing, stays less than some threshold epsilon. And the minus log of this type 2 error is what is sometimes called the hypothesis testing relative entropy, and written like this. You can show that it satisfies data processing, so there's some reason why you might want to choose this notation. And why do I look at the negative log here? Essentially, what is also very often looked at is at the source setting where I have many copies of my state. So I want to just discriminate many copies of my state rho from many copies of my state sigma. And then I want to look at kind of the decay rate of my error with the number of copies I used. And then this will just be 1 over n times this negative log. So it makes sense to look at the logarithm in that sense. And okay, so we can come back to kind of our two ways of writing down, a setup for our channel discrimination task. And as I said previously, kind of you use your channel n times, and at the end you will arrive at some kind of state. And the state will be different depending on whether your black box is E or F. So if your black box is E, here you're going to have E of rho, and then your E only acts on this part of your state, and then on this bottom part you act with identity. So you'll have this state. And if your channel happens to be F, then you will have this state instead. So kind of at this stage you can reduce this to this state discrimination problem. And then the type 2 error rate per channel use, such the type 1 error still stays below epsilon. So you have to be given by this quantity. And you compare this to the parallel strategy, where, again, I look at the two possible options I have at this stage here at the end after my channel uses, depending on whether my black box actually is E or F. And so I have to discriminate between these two possible options. So I have E tensor N acting on my joint input state mu, or F tensor N on my joint input state nu. And from now on, I'm not going to write these identities on reference systems anymore. I'm just going to kind of write things like this. So yeah, so the question is, how do these two quantities, which I just wrote down, so this one and this one, are related to each other? And people looked at this previously by looking at kind of the asymptotics if n goes to infinity. So what people have been able to show is that if I optimize over all possible sequential strategies, which essentially means I optimize over the first input state here, and then over all these preparation maps lambda, and look at the this type 2 error rate for the adapter for sequential case, and then look at the limit n to infinity and the limit epsilon to 0. What this means is I look at the asymptotic rate such that my type 1 error also goes to 0. This is what this putting this first limit here does. Then you can show this is equal to the what is called the amortized divergence. I'm not going to like write on the definition; it's not really important. This was done by Wang and Wilde. And then in this chain rule paper, Fang, Forsi, Van, and Sutter were able to show this amortized divergence is actually equal to the regularized divergence, which is given by this limit, where I look at the parallel exponent, get optimized over all parallel strategies, so all input states. And then again, the same type of limits. And this was maybe a somewhat surprising result because people have previously shown that in some different settings, for example, if you look at the symmetric case where I don't have this thing, I want to minimize my type 2 error under the constraint of the type 1 error, but I want to minimize the sum of the two. Actually, adaptive strategies in general also asymptotically will be better than parallel strategies. But okay, people have been able to show this. And kind of what we would like to do is, okay, I mean, this asymptotic result is nice, but we kind of want to know what happens at finite n. So if I say, okay, I only want to limit myself to some finite number of channel uses, what can I say? How much better can adaptive strategy be? Or like essentially the same thing. If I want to restrict myself to parallel strategies, how much worse is my rate going to be? And so in a similar direction, I mean, from this purely asymptotic statement, it could be that this first limit converges way faster than the second one. So just to achieve the same rate, you need a way bigger number of parallel channel users and sequential channel users, and whether you can say something about kind of the relation between these two. And so we were able to show something by this, and our theorem is the following. So let E and F be two channels such that this condition holds. And I'm just going to ignore this for now. I'm going to come back to this condition in a second and say maybe why this is like relevant and why it's maybe not very surprising. Then given an adaptive strategy, so remember my notation was that these for I and sigma I were the states you have in your adaptive strategies after using the channel a certain number of times. So somebody gives me an adaptive strategy, then I'm going to construct a parallel strategy from this, and I'm going to construct it like in a very general sense. So I'm going to construct a parallel strategy for every possible number of parallel channel users. And also I allow you to essentially pick type 1 error thresholds. So previously these were epsilons, now I call them alpha S and alpha P as you want. And I do this in such a way that my parallel rate, so this here is the essentially type 2 error of my parallel strategy, such that my type 1 error is less than alpha P and then taking the log and 1/m. So the decay rate per parallel channel users is bigger than, so it kind of makes my parallel strategy is pretty good, is bigger than this thing, which except for this prefactor here, which is small, if my type 1 error is small, which kind of you generally want to be in this setting. This is the type 2 error decay rate per channel use of my original adaptive strategy, and then I have an error term. Okay, what does this error term look like? First of all, the error term is this logarithm with 1 alpha P in it, which is generally to be expected, because if I make my type 1 error threshold of my parallel strategy small, then kind of this also gets small, so there has to be some kind of trade-off. But then I also have this n over square root of m, which to some degree tells me, okay, if I kind of make my m very large, so if I choose a parallel strategy with very many channel users, this term is going to be small, but kind of m has to be at least a lot bigger, not just at least, it has to be a lot bigger than the original number of sequential or adaptive channel users I had. This kind of, to some degree, gives at least the bound on the original question, okay, how much how many more channel uses do I need in a parallel setting compared to an adaptive setting for them to be comparable? And then there's this constant C, and this constant C still depends on E and F. And this is not the tightest bound you can give. We have some tighter bounds in the paper, but it's kind of one which is easy to write down. So you can write in terms of the two Petzvenny entropy, also in terms of the max channel relative entropy. I'm going to define this in a second, if you don't know what this is. So yeah, let me very briefly come back to this condition here on the top. So if this condition doesn't hold, so if these two are equal infinity, then in some sense, E and F are perfectly distinguishable eventually if I have enough copies. In the sense that I can choose one of these two errors to be 0 and the other one will always also then go to 0 eventually in the limit. And if you don't have this condition, you can show that there actually exists adaptive strategies which have an infinite exponent after a finite number of uses. But if you make your type 1 error small enough, so kind of for every m, there exists a type 1 error which is small enough, so this thing cannot be infinite. So you cannot really have a relation like this. But maybe also this case where this is equal to infinity is not so interesting. Because then, yeah, I mean, eventually you will always have type 2 error equal to 0. Okay, so next I would like to briefly talk about how you actually prove this. So essentially, kind of what you have to do is you somehow have to, convert this entropic quantity where you have two channels with different input states to one where you have two channels with the same input state. And this uses something which people call a chain rule. And what you can use, you can prove these chain rules fairly simply for the max and the smooth max relative entropy. So what is the max relative entropy? It's defined as the logarithm of the smallest real number such that your state rho is less than lambda times your state sigma, less than positive semi-definite order. And with this definition, you can fairly easily prove this chain rule for the smooth max, for the max relative entropy, which basically states that kind of this relative entropy between E of rho and F of sigma is upper bounded by the difference of the states in a sense, and then the difference of the channels when you value on the first output. And you can kind of prove something very similar for what is called the smooth max relative entropy, where you take this max relative entropy, but then you take the infimum of it over all states rho tilde, which are epsilon close to rho. And I mean, stress this here, what we do here is we take this epsilon ball in purified distance, but only over normalized states. People sometimes do this differently. That makes the expression a lot nicer here. And with this definition, then you can prove, and I'm going to do this in a second, a chain rule for the smooth max relative entropy, where you get essentially the same structure, although your state mu here in the second term is not going to be rho, but something epsilon close to rho. And then here, the smoothing parameters add up. Okay, so how do you prove this? Essentially, what you do is you start with this definition of the smooth max relative entropy, which tells you there is a state mu, which is epsilon close to rho, such that this condition holds. And then, because F is a positive map, I can apply it on both sides. So I get this. And now I can do the same thing, but with this smooth max relative entropy, where I look at the difference between E of mu and F of mu. And again, I'm going to get a state tau, which is now epsilon prime close to E of mu, such that this condition holds. And now I can kind of insert this expression I have for F of mu into here. And I'm going to get this expression, which is essentially already what I want, because now I know that I have a bound. I mean, this is just a number relating tau and F of sigma, and I want something which is a smooth max relative entropy of E of rho and F of sigma. So the last thing I just have to show is that this tau is also epsilon plus epsilon prime close to E of rho. And this I can do by essentially just using the triangle inequality and the data pressing inequality for the purified distance. So I express the purified distance between tau and E of rho as a sum of the purified distance between tau and E of mu plus the purified distance between E of mu and E of rho. And this first term, by the definition of tau, is less than or equal than epsilon prime, because there was an epsilon prime here in my smooth max relative entropy. And then I can use data pressing inequality for the purified distance here to get rid of the e's. And then again, by the definition of mu here, I get an e for this term. So I get this. So this is fairly simple. But now what I actually want to show is a relation for the hypothesis testing relative entropies, so essentially type 2 errors and not smooth max relative entropies. So somehow I have to convert between these two. And there are relations with which you can do this. One of them is the following, which has been shown in this paper by Anshu, Berta, Jan, and Tomomichi, which basically tells you that the smooth max relative entropy, where you smooth with epsilon, is upper bounded by this hypothesis testing relative entropy with type 1 error 1 minus epsilon squared. And turns out we also need something else, which is this relation, which is kind of fairly well known because it shows up in converse bounds in kind of all hypothesis testing tasks. A lot of papers where essentially relate the hypothesis testing relative entropy to relative entropy modulo some small error terms. And it's maybe not entirely obvious why I actually want to do this, why I want to go to relative entropy, but it turns out we kind of have to. Yeah, I can maybe talk about this a bit later if there's some questions. And then for this relative entropy, we also want some bounds relating this to the smooth max relative entropy, which are known as the asymptotic equiaddition property. So what it essentially states is that if I look at the smooth max relative entropy taking many copies of 1 sigma divided by 1 over n, this is essentially equal to the relative entropy of 1 sigma modulo some error terms, which decay with the square root of n. And this kind of first relation with a slightly different error term was known for quite some time. Been shown in this paper from Marco Tomomichi. Although the second one I couldn't find anywhere, so we had to basically prove this ourselves. And in the process of doing this, we kind of found a slightly better error bound here, which uses these Petroni entropies of essentially an arbitrary order. But this may be like a minor thing for people who care about these technicalities. So kind of having all of this, I can actually kind of give you like somewhat of an outline of the proof of our theorem. So how do we start? I start with this hypothesis testing entropy in the adaptive setting. So this is essentially, if you kind of forget about this 1 minus alpha s term here, the type 2 error decay per channel use for the adaptive strategy we start with. And I can use this bound, which relates this to relative entropy, to kind of convert from this hypothesis testing relative entropy to relative entropy here. And the reason I'm doing this is now that I want to exploit this structure of how our adaptive strategy looks like. Essentially, what I'm doing here is I can write this relative entropy of the two states here as the difference between relative entropy of the two states here minus the relative entropy of the two states here, plus then the difference of the two states here minus the two states here, and so on. But then here, I'm just applying a channel which kind of act the same way on this part and this part. So actually, the difference here is going to be negative, so I can forget about it. And so I arrive at this expression. So I can write this as a sum of these differences. And then we don't actually have to do this next step, but it's very convenient. We can say, okay, I bound this 1 over n times the sum by the largest element, which I'll call, the index of which I'll call L. And just have this expression. And now going from here to here, I can use these AEP bounds to arrive at a smooth max relative entropy where I now have m copies of my channel and m copies of my state. And yeah, I need both directions here because one term comes with a plus and one term comes with a minus. And finally, now I can use this chain rule I proved for the smooth max relative entropy to kind of take this difference. Well, here, you have channels with 2 different input states, and you have the 2 input states to this term where I have 2 channels with the same input state. And what is kind of conceptually crucial here is that because this state mu is not L tensor m, but just kind of epsilon close to it, we actually have some potentially entangled input state here. And we need this because you can show that kind of to achieve optimum rates and channel discrimination, in general, you need entangled input states. And then finally, I can use this relation between smooth max and hypothesis testing relative entropy to go to this term. This is exactly what I wanted in my theorem. So this is some kind of brief overview of the proof. What kind of is the technically hard step, or maybe kind of also in some sense the interesting step, is to show that these dots here actually give you the error terms, which I claim that you get. But yeah, that's something which we do in the paper. I don't think it's really something you can do in a talk. So yeah, this proves a theorem. Maybe like from a conceptual perspective, what actually, how does my parallel strategy end up looking like? What really is my input state in the end? So one way you can think about it is that you can take your sequential or adaptive strategy and take it m times in parallel, And then, you look at this one step where distinguishability and relative entropy increases the most, the step L. And you look at the two possible options here for a state here. You will have the state rho L tensor M here if your black box happens to be E, and the state sigma L tensor M if your black box happens to be F. And you can take the state and you can slightly modify it by making, so you take the state rho L tensor M and you slightly modify it by making it a bit more similar to sigma L tensor M. And in this process, first of all, it's not going to be IID anymore. And kind of also the degree to which you make it similar to sigma L tensor M depends to what degree you want to accept the type 1 error. The argument goes a bit in the way that you say, because your sequential strategy is kind of good at kind of certifying E at this point when you have the state L tensor M, you'll have a small type 1 error if you just keep L tensor M. And then if you make it a bit more similar to sigma tensor M, you're going to maybe increase the type 1 error a bit. So depending on what type 1 error you want to accept, you're going to move the state a bit further over to sigma tensor M. And this is going to be the state that you choose in your parallel strategy, and it can be proof you get the corresponding bound if you do this. Okay, how much time do I have left? Okay, I have 1 minute, so I'm going to skip over the example and just go to the open questions immediately. So there's kind of interesting open questions still to be talked about here. So maybe kind of the most obvious one is, I showed you this bound that generally in the least of the order of n squared parallel channel users, if n is the number of adapter channel users you have, they kind of get a similar rate. And it's not at all clear whether this is optimal. Kind of intuitively, I would say it's not, but it's kind of not so easy to kind of show something better. We tried a little bit, and what we think we would need to kind of get away with this n term in the numerator is some kind of convergence bound on the regularized relative entropy. So kind of knowing, in this limit where I take n copies of the channel, how many copies of the channel do I really need in this limit until I get close to the limit? And I don't think there's any result currently available there, and it's not so obvious how you prove that. But if you had this, you could probably kind of find a way to get, or at least kind of decrease these number of parallel channel users you need per sequential channels. And you would probably get something similar if you had some kind of boundary convergence, the amortized divergence. And maybe something also which maybe some people who kind of know about this have asked themselves, okay, like, why doesn't he use second order expansions? Isn't this kind of way better than all the stuff he did? It kind of is. But if you want to, so the problem is that because you have entangled input states in your parallel channel users, the things you get are not IID. And if you want to use second order expansions, you need to have some kind of control over these variant terms when you have these non-IID states either from the adaptive side or from the parallel side. And if you kind of get some control over these, essentially show that these only grow with the number of channel users linearly and not quadratically, then you actually get a lot further than what we did. And I'm pretty sure you would also be able to prove some converse and channel discrimination, which seems to be a pretty hard problem people have thought about for the last couple of years. So this is essentially why we kind of have to do something a little bit different and arrive at the bounds that we get. So yeah, that concludes my talk, and I'll be very happy to take questions.
Thanks a lot, Beyond. It's really inspiring talk. Yeah, we got a couple of questions. David, please just go ahead.
So thanks for taking the question. I want to argue that the case when the adaptive strategy suddenly gives you a perfect strategy, while the parallel strategy never will get there, already answered your first question.
You mean this first open question?
Yes. We have an example from 30
I guess so.
Two users already got perfect, and you never get perfect with parallel strategy, right? But you dismiss that case with the
I guess that is true.
Condition that you need in your theorem.
I guess that is true. Yeah, okay, I'm happy to accept that. I guess kind of the question is then, if I put in the condition, what happens then?
But what I want to argue is that you seem to have dismissed a very interesting case when the adaptive strategy can do something that the parallel strategy can never achieve. Yeah, I don't know. I think this example is extremely interesting, and I don't want to in any way claim that this is not relevant or something. But I mean, I guess kind of
Now, what happens in this case, I guess, is that also the if you look at this asymmetric parallel exponent, it will also become infinity. And so, I mean, in that sense, these strategies are still equal, even though, okay, it takes kind of an infinite amount for the parallel strategy to get there. And I guess in that sense, you show, okay, in this specific case, there is no kind of obvious relation between the number of parallel and sequential channel uses you need to kind of achieve some kind of equality, because one is finite, one is infinite. But then, okay, if I look at the case where it's not infinite, but like, okay, I guess that's kind of by way to say it. If I look at the case where kind of my condition holds, at least right now, I can kind of show some kind of square root relation. And I would like to know whether it's tight, independent of, you know, this maybe just from a mathematical interest. Did you kind of get what I'm trying to say?
Yeah. And related question is that, do you have a way, do you have an algorithm or a procedure to find out whether there is a perfect strategy or not?
You mean in the adaptive or parallel case?
Yes, in the adaptive case.
I think that not that I've thought about this personally, but I think there have been some papers about this by.
Yeah, now that I asked that question, I think maybe Ren Yao and his collaborators have a characterization. I just can't remember. I think they certainly have other examples.
Yeah, I mean, something which I think is kind of interesting and a little bit. I feel like so far the only like actual examples we have where we have perfect distinguishability with adaptive strategies are when we have only 2 adaptive channel uses. And kind of what we would like, for example, if you want to benchmark this, something we would like to have would be something where, you know, this is not 2, but maybe like an arbitrary large number. And I'm not sure if you can easily construct examples like this. Like I thought about it for some time, and I couldn't immediately.
We wrote down some examples. We just have no proof.
Oh, okay.
That's why I'm interested in knowing if there's a way to.
So I think there have been some papers and on characterizing also the adaptive case. When you have a perfect discrimination, and I want to say it is exactly when this condition holds that these D max is infinity, but I'm not entirely certain anymore. But there should be some. I can send them. I can find them and send them to you later. I can't remember the exact like authors or titles right now. But
it would be nice to know if there is a way to.
I think that people. I think people have done something in this direction.
Thank you.
Just from a layman's perspective, are you talking about the case where you have 2 unitary channels?
Yeah, I guess also there's been a lot of study in this regard. I guess kind of a bit more interested in the general case, you have maybe also, for example, the unitary cases.
Thanks, Daddy, for the very helpful comment. I guess Hayashi-san has some question.
Sorry.
That's Hayashi. Yeah.
Did you discuss case of Pauli channel? I think this is not so difficult. No.
Sorry,
I'm confused. So, Debbie and you discussed the case about the Pauli channel. No.
Sorry, I have a very hard time understanding you. Maybe if you talk a tiny bit slower, that will make it.
So sorry, Debbie and you discussed the case of Pauli channel. Pauli channel.
The case of Pauli channel.
No.
No, we didn't really talk. We didn't really talk about Pauli channels. No, we were thinking about cases where adaptively you can perfectly discriminate channels with a finite number of channel uses. That's what we were thinking about.
Finite number, perfect. Okay. So I have another comment. So you consider second order expansion, but I think even in the classical case, this is open.
Sorry, say the last part again.
The classical channel discrimination, still this kind of second order is open. So I tried this one, but I could not. So
I mean, essentially, what I'm saying here, second order is awful also for the quantum case. Like I don't know how to do second order, that's why I'm not doing it. Because essentially, kind of these correlated input states kind of make everything pretty. Like you have essentially no way to control these error terms you get, and this is why even though of course I would like to use second order because the bounds you get are so much more tight, I don't really know how to do it, and this is why I kind of have to do these other things with these kind of more loose AEP bounds and things like this.
Of course, in the case of classical stone converts forward, but the second order is still quite difficult.
Yeah, I can see that. Yeah.
Okay.
Thanks, Niranjana. Maybe.
Yeah, this is more in response to the comment you made, Yushang. You asked about unitaries. Well, regarding unitaries, it was already proved by Antonio Asin that they can be perfectly discriminated even in the parallel case with a finite number of users,
I see.
right?
I see.
Duan et al. Did adaptive case. So just wanted to make that comment.
So in that case, both are infinite. It's not really the thing that so it's different thing.
Thank you.
Okay, I see. Thanks. If there's, Debbie.
Yeah, sorry, one more comment. Whether the two channels can be distinguished perfectly adaptively was found out by Wen Yadun, Yun Feng, and Mingsheng Ying. In 2009, there is a criterion there, but it would be nice to compare with your condition. And I think it does not say how many copies you need.
If I
it does not
correctly,
specifically say how many copies, but it does say whether it is finite or infinite.
But I think you can, not entirely sure, maybe this was the parallel case. No, maybe I'm misremembering things. Maybe I thought there was a way sometimes you can get like a very, very crude bound, but maybe there's also, I'm misremembering things.
In the parallel case, you can use STP bound. I think that's how we do one situation that you cannot do that perfectly.
I also thought in the adaptive case, you would have some kind of weird, no, actually maybe, I'm not sure anymore.
There is a different, let me mention that there is a different STP that you can use in the adaptive case. That's resolved by Chirabella and collaborators on the notion of these quantum comps. And in some other branch of quantum information, they call it the quantum strategies.
Okay. Okay. But yeah, okay. Well, thank you very much.
Yeah, we can discuss more offline.
Yeah, sure.
Oh, maybe just one last chance for Niranjana.
Yeah, just a little comment. No, I just wanted to point out that. Just one last comment to say that what is nice about Beyond's work is not to giving the more general question that if you're given any sequential strategy, can you then come up with a parallel strategy which has the same error rates? Yeah, because the parallel strategy is easier to implement. So I think that itself is the appeal of the result. Thanks.
Thanks for the comments. Yeah. Okay, I think we are slightly over time, but luckily we don't have any other schedule right after this. So, so with this, I would like to take this chance to let's thank all the speakers of this session. Thank you very much for delivering these 3 very interesting talks. And to everybody else, hope you have a nice day / evening. Okay, see you tomorrow.
See you. 힘들다.